All right. Hello and welcome, everyone. Welcome back to the second Applied Active Inference Symposium. It is the second interval, and it's July 31st, 2022. In this second session, we are going to first feature a presentation by Bruno Lara, Prediction Error Dynamics, a Proof of Concept Implementation. Following that, we'll hear from Matt Brown with a presentation, Real-Time Robotic Control through Embodied Homeostatic Feedback. The third presentation will be by Adam Safron on Generalized Simultaneous Localization and Mapping, GSLAM, as a unification framework for natural and artificial intelligences. And the final presentation will be by J.F. Cloutier towards a symbolic implementation of active inference for Lego robots. We'll then have some of those presenters rejoin us in the final 2 or so hours of this interval for a roundtable discussion. We'll also be joined by Karl Friston there. So thanks everyone for watching live or in replay. Hope that you add any comments if you would like into the live chat. And otherwise, thanks to all of our presenters and co-organizers for their awesome work. And thanks so much for joining, Bruno. Please take it away.
Yeah, thanks a lot, Daniel, for the invitation. I was very surprised, as most of our work so far is not directly related. Well, it's not actually active inference. Of course, it's related. But since we published a couple of years ago a paper that actually I'm presenting a bit of these results here. Well, lots of nice and interesting people started to look into this implementation of prediction error dynamics, and it's actually the part where we could say it's the part that we are taking out of all this framework to try to implement in our robots, in our agents. I don't know how much or how many times you've heard this story of why we are doing this kind of cognitive robotics, or why we like to call all this research or this area cognitive robotics. And I like a lot this slide, which kind of summarizes what it's usually a long introduction on the history of artificial intelligence and robotics. And it just tells this story of 50 years of research trying to figure out how can we have machines that are as intelligent as humans. And it comes out that actually this upper part of the image quite got resolved rather fast. We cannot say easily, but it was more or less fast. And then we have the second part of the slide, like the bottom part, which is what comes out to be the most difficult challenge for robotics. No, so what has to do with interaction with the world. You have a small child that is capable of handling these objects in the environment, and then you have this other robot that can do it. But at the moment that you change the size, the weight, the position, whatever you want of the pieces or of the chessboard, you actually have a child that with no problem can adapt himself to the challenge, you know. And the nerd joke is then on the other side you have another PhD that has to solve it if you do the same for the robot, you know. So in reality, what was supposed to or was thought to be kind of the hard problem, which was having a robot reason and solve problems, it came out to be quite the not so difficult to solve task. And we can talk about more difficult challenges that have already been passed, such as, I don't know, playing Go, which is way harder than chess. And we had AlphaGo a couple of years ago, well, winning against the human champion. So we like to think that we are doing now things differently. We are having robots that interact with the world, that interact with what's going on around, and they learn through this interaction. And of course, that gives us lots of challenges and lots of things that we have to solve. So now I come from this. Yeah, you could think now as an old school of internal models. We work in this field for quite already some years, and it's this part of the world where there is inverse and forward models, for control, of course, and they are thought to be behind all these important issues in humans. Since the beginning of my career, we've been doing implementations of different types of tools for these robots, but always based on these inverse and forward models. So just a quick reminder for those that might not be very much into this type of models. So we had a sensory situation, whichever it is, whatever it is, and we have a desired sensory situation. We have an inverse model that takes as input those two things, the sensory situation at time t, of course, the sensory situation at time t+1, which is the desired. And the inverse model is going to tell us what's the motor command that needs to be performed to go from here to here, right? And then we have a forward model that takes the sensory situation at time t and the motor command at time t and gives us the prediction of what's going to happen with this sensory situation. And so we have a prediction error when we have lots of errors, but we are interested on particularly this error, which is the difference between what we actually predicted and what happened in the world. So we've been doing this for quite a while. Well, we've also used this prediction back as a sensory situation, and we can get long time predictions, what we called. We can do lots of comparisons between what we wanted and what actually happened, and lots of different errors. But as you know, and well, now everyone works with, is actually this error, like the difference between the world and what actually I predicted. Yeah, and so that's what we can say we have in common. Some years some years ago, actually, we came across all these ideas of prediction, predictive processing, and we started to dig into it to see what actually we could use for our models, what could be useful for improving our models and our agents' behaviors. And we have lots of doubts, lots of questions. But one of the first things that we've done so far is to look into what happens with the error as an agent is executing an action. Sorry. But first, I'd like to walk you through one of our implementations. Well, first, where is actually the what you could call the cross areas of what we believe it's important in this case, when we have active inference and prediction error minimization. So most of us are very familiar with this kind of representation of what's happening actually during action, and we actually believe that minimizing prediction error is what leads to belief updating. So like the change in a prior belief encoded as a posterior belief, and this is actually informational gain. So this means learning, right? So in active inference, the expected future states are fulfilled through action execution, we know, and this associated expected prediction error is minimized by actively sampling sensory information. And so the important part for us is this expected prediction error. And we believe the attribute of a policy, which can be epistemic and instrumental, in case this action is novelty searching, it's reflecting its epistemic affordance, and we could say it's acting for information. In case of preference searching, no, this reflects instrumental affordances and its action for reward. So, in words of Kirvenstein, we can think of active inference as the process of selecting relevant affordances. So those which are expected to minimize prediction error in a context-sensitive manner. Yeah. So what we've done actually, or what we wanted to actually implement is how these expectations about the dynamics of the error cause or are related to feelings, to these embodied feelings. And we believe they allow a sensitivity. So how well or how bad an agent is doing at improving the grip on what is relevant in the landscape of affordances. So the sensitivity to changes in the rate of prediction error reduction is what we call prediction error dynamics. And we can say the steeper the slope, the faster the rate of reduction. And we see some like examples, just very simple. So in black we could see the actual error as the action is executing, and then we have a slope associated to this error. So what we don't want, what the agent doesn't want, is this error increasing, having a positive slope. And on the other hand, the error is decreasing, then we have this slope, and this is actually what we are looking for. So prediction errors are manifested as changes on affect. So if the rate of prediction error is faster than expected, we have a positive balance, and we have an action policy which is more precise. In the case that the error is slower than expected or is increasing unexpectedly, we have a negative balance and an action policy which is less precise. So just walking you through a couple of implementations that we have done. The first one is just kind of an example of this mix that we are trying to have. The error is used for learning, but we have a very simple implementation of self-organizing maps. We call it the self-organized internal models architecture. The nice thing on this architecture is that it actually sort of doesn't have to have an inverse model. What we have is an self-organizing map that organizes the motor sensory information. And on the other hand, we have a visual sensory information, which is also organized in the same, another self-organizing map. And then we have what we call a multimodal representation. And in this multimodal representation, we have associations. We have associations between a sensory situation, another sensory situation, and a motor command. So you could think of this as an inverse forward model pair, but it's actually not encoded as such. So we just have associations between sensory situations and motor commands. So we thought this was very interesting, and we use it, for example, for saccadic control. So the robot has some initial sensory situation, which is the stimulus somewhere in its field of view. And what we need, or what the robot wants, is to foveate the stimulus. No? So this is the sensory situation, the desired one. And we ask this self-organizing maps architecture what we need to do so to bring the stimulus from here to here, and it's executed. It's not very precise, so it comes close to the center of the image. And then we use this as the new sensory situation. Then we have the same target. We again ask the architecture what do we need to do, and then it comes very close. So after 100 runs, you can see that the robot, this is the starting situation. In red, we have the first prediction and execution, and in green, we have the second prediction and execution. So it's a very nice, simple architecture that actually works, as I said before. It works like a forward model, but it can also work as an inverse model. We use prediction error to learn. And so we could use it as some kind of modular architecture. We can put more maps. And in this case, we have the position of the head, visual stimulus, the position of the arm. And what the robot can actually do is find the stimulus somewhere in the space and then bring it to the center, kind of obviate it, and then actually bring the arm also there. So we have all these associations between movements of the head, movements of the arm, movements of the eyes, and all these get associated and are coded as initial and ending positions. Okay, so the next question or the next thing we tried to do was how can we use prediction error dynamics to guide learning? And this paper we presented a couple of years ago in Epirob. It was actually Guido Schillaci that presented it, which is our co-author. So it's a work well, by Guido, Alejandra Siria, which is also a colleague, and myself. And what we did there is, I won't work on the. I won't tell you much about the maths or the kind of networks that were used in detail. The important part is what we see here. So we have a very simple robot. This is what you could see here. It's a two degrees of freedom camera mounted on a sort of artificial field where we have lots of plants, and the robot moves towards a specific destination. So it wants to look at some image, at some plant. And so we have for each movement, for each goal, we have a prediction error here. So we organize the goals in a sum. Of course, the goals, are encoded using an autoencoder. We use the middle part of the encoder to have represented the goals here. And the important part is each one of these goals has some prediction error dynamics. Yeah. And so we go back again to our inverse model and forward model and execute the command, the motor command, and we get we do our prediction, and we get an error between what we wanted and what happened. The interesting part and what became kind of nice, and that was what we wanted to implement, what we were thinking about, is we append this prediction error to a sort of a buffer. And this buffer, once that it contains more than 4 predictions, we do a linear regression, and actually what we get is an indicator of the progress. How good are we doing? So it's kind of a tendency for learning. So when we have a negative slope, it actually means we are going towards the goal. We are doing fine. So progress is increasing. It means there is a positive emotion, and we remain on this goal. So learning is going fine. When the slope is positive, so the activity is away from the goal, there is no progress, the error keeps increasing. So we have what we could see as a negative emotion. Something that can be encouraged is then to switch goal. So we have a positive slope means increase the size of the prediction error dynamics buffer. This was one of the sorry, that was something of kind of interesting and very new in this field, in this area. We haven't thought about it before, and what we actually did is, okay, what happens if my slope is positive? It means I'm doing very bad at this task, and what I'm going to do is I'm going to increase the size of this buffer. Yeah. When we have a negative slope, it means, okay, I'm doing fine, so I'm going to decrease the size of this buffer. So what we are actually doing is adjusting dynamically the size of this monitoring window, and we are doing that depending on how things are going with respect to what we are actually expecting. So if the prediction error increases, we have a positive slope, and we do a more frequent evaluation of the feedback. This allows a quick correction of the action, and it can lead to satisfaction in case we manage to do it better, and induces abandoning the goal. So in this case, after a number of interactions, where the error is not decreasing, the error keeps increasing, then we can switch goals, and we could say we are trying to avoid frustration. So through intrinsic motivation, what we try is search for a new goal. When the prediction error decreases, we have a negative slope. We don't need to be evaluating the feedback so frequently, and we can free resources for the agent to do something else. There is no more prediction error, so that means we've achieved our goal. So learning occur. Again, we search for a new goal now. So when we select a new goal, we give priority to those that have a negative slope, which is kind of steep in the prediction error dynamics. And we have some examples here of how the error moves as we are moving in the world, and how the buffer size increases when the error increases, and then it decreases when the slope now again changes. So that was one of the first things we did, and now actually Adam invited us to this special issue that he did in Frontiers, and we published there a paper, which is actually, well, at the beginning it was about something else, and then we ended up with this model, presenting this model. This is just an idea that we have, which actually encloses this part that I talk about the slopes and the expected error. So what we are suggesting here is that I don't know how much time we have, if I can go into detail on this, but let's try something very fast. So we have an agent that has maybe physiological needs. In case the agent doesn't have physiological needs, through intrinsic motivation, we want to do something new. We want to do search around the world. Then we go to what we call the environmental context, which brings us to this field of affordances, where there is loads of actions, and each action, each task has some expected error dynamics. We go to a task-related context, which comes from selecting the task, and then we do some planning of sensory motor sequences. We start acting on the world, and we get some error. As we execute this task, then we have two types of monitoring. We have the typical momentaneous, say, error that helps us go through the planning and correct the execution of the task. And we have a window of prediction error dynamics, which is compared to the expected error that this action had. And according to that, is that we are going to go to these emotions that tells us, no, the error is increasing. We have this slope here. So we go back to another task before, like, of course, checking then if something has changed, we still have physiological needs or we don't. If the error is not so gravely increasing, it's more or less going fine, then we go back to this same planning, to this same action. So it's a very nice model that we thought of. It's on the make, and we have many ideas from bringing this box diagram into the world, and in our idealistic dream. What we are thinking on is something actually based on SOIMA. We haven't implemented this yet, but it's something based on this SOIMA. But now we have lots of other modules. We have some interoceptive internal model representation, exteroceptive model representation. This is actually wrong, but anyway, so in this side, we have all the exteroceptive information, the interoceptive information, and we have some policies and a task and some error. This error is going to tell us how we are doing, how we can stay on the task. If the error is too big, then we can change tasks. So it's a bit of a mixture between the previous thing I told you, and this is how it could look in what happens on a top down. So when we have a task, this task is going to activate some policies, and these policies are going down to act on the world. We have again some error coming up, and this error is somehow coded here. There is some monitoring so that we can go on in our policies. This is the momentaneous error. If the error is very big, then we can go back here. Sorry. So this is top down, and this is actually bottom up. No, it's actually the error coming up all the way and coding here. And yeah, and this is how we start the cycle with some task policies and everything else that is happening in the world. So I think that we can stop there. I hope it's clear. We don't have direct questions from the audience, as I'm not seeing anyone. Or
I'll ask one question. Otherwise, no, we have no direct questions, but we can definitely accumulate them for the roundtable.
Yeah.
What is the relationship between prediction error minimization and free energy?
Well, I think it's just like part of the process. I don't know what you mean. I mean, within the whole thing of whatever you want, free energy, everything that is happening, the difference between the expected states and what actually happening in the world. So we always have in active inference or in free energy, you always have an error happening in what's happening, what is happening in the action of in the world. So through this prediction error is how we believe it's going to happen, like the learning is going to occur. I don't know if...
Yes, that's awesome. Well,
yeah.
Thank you very much. Hope to see you very soon.
Yeah, we'll see you like in 2 hours or so.
Excellent. See you soon.
Yeah.
Thank you very much. Hope to see you very soon. All right, welcome everyone. We are back. This next presentation is going to be by Matt Brown, Real-Time Robotic Control through Embodied Homeostatic Feedback. So Matt, thank you very much for co-organizing and for also joining to present, and please take it away.
Yeah, thank you for having me here. And that was a really great talk, Bruno. I have some follow-up questions for later. But yeah, thanks for coming. And my name is Matt. I'll be talking a bit about a long-running research project, and I hope you guys find this interesting. Here's a quick high-level description of the project. It's kind of an alternate way of looking at the generative modeling process built around homeostasis from the bottom up. This approach is very different, a bit of an unorthodox approach, and I'll be going into a bit of detail about how this works. You can probably read it, but the short version is based on theories of Ross Ashby and his homeostat, and it's a new kind of adaptive model that uses learns via homeostatic feedback through an environment and itself. And I'll be showing some demos about applying this to robotic control that I've been working on lately. Just a quick agenda. I'll be talking a bit about the project background, where it came from, because it is kind of unusual. I figure some background might be useful. Then I'll be talking about how homeostats build network self-models, and what that means and how those function. And then I'll be talking about plugging those into environments and how embodiment works and how synchronization functions in this process. And then I'll be doing some demonstrations showing this working with robotics. Yeah, so just to give you background on myself, I'm a computer scientist mostly. I'm not much of an academic. I have a few published papers, but none on this particular topic. I've been obsessed with the mechanisms of thought for most of my life. I've worked in the video game industry for about a dozen years, and then worked in deep reinforcement learning for a number of years. And also about 20 years ago worked in software radio at the Spectrumware project, which became Genie Radio. That'll be relevant later. Today, I'll be talking about work that's now ongoing at my startup ThoughtForge, and talking a bit about the history will help explain what I'm doing, I think. This started about 2006, 2007 with deep learning was kind of new and was kind of the new hot thing. I did a big deep dive into it, really excited about it. But I was, in fact, quite dissatisfied, and I felt that deep learning and this approach of using neural networks didn't really provide much insight to how learning works in natural systems. And even in the last few years, I feel like we have this amazing hammer with deep learning, and everything suddenly looks like nails. And I feel like we need to take a step back and look critically at what we're what problem we're trying to solve. So for me, I was looking for new approaches in the nature of agency and goals. Goals in terms of what are they and how do they manifest in nature. Semantic information versus raw information. How do raw sensory signals become meaningful? And also, I wanted more insight into how time played into this learning process. And I was in particular looking for medium agnostic approaches, not neuron specific. How do plants and single-celled organisms deal with their world? So I started by reading a lot. Going back in time, chaos theory, I was a big fan of. I ran into Maturana and Varela and autopoiesis, and I was really excited about that, but it was too abstract for me as an engineer, I think, to tackle. And so I kept going until I got to homeostasis and cybernetics, and particularly a cyberneticist named Ross Ashby. And I basically became obsessed with Ross Ashby, and still am to a certain degree. And he's not a part of most computer science programs, so he's quite well known outside of computer science, but I felt is not part of my own education. And he's most known for things like the law of requisite variety and the good regulator theorem, and those will be common themes in the next 30 minutes or so. So what I started doing is pouring through Ashby's technical journals, recreating his work, and in particular a device called the homeostat. So this is just a quick slide to tell people about the homeostat and Ashby. No doubt many people watching this probably are familiar with Ashby and perhaps the homeostat, but it's worth going over briefly regardless. If you look up on Wikipedia, it'll say homeostat is one of the first devices capable of adapting itself to the environment, and it exhibited behaviors such as habituation, reinforcement, and learning through its ability to maintain homeostasis in a changing environment. Ashby viewed it, learning as adaptation and stability. And was described as an isomorphism generating machine. And most importantly, for me, it uses feedback to generate homeostasis via a property called ultrastability. So I'll be talking about that here. There's a description here from one of his books about it, but it is quite tricky to reproduce. I had to go to his personal technical journals and lots of iteration before I got it working. The key for me was ultrastability, which is a very strange kind of property, but it is the individual node property within this 4-node homeostat that enabled this general property, this group property of homeostasis to take place. And it's core to the function of how, let me go back. It's core to the function of how the homeostat works. And it's in the property implemented by individual nodes using a simple set of rules that gives rise to group homeostasis. It's comprised of a double feedback loop, where like the low-level feedback loop performs like a linear transformation, and then a high-level feedback loop modifies this linear transformation, and is designed to seek equilibrium, meaning output of 0, which is, you can, if you think of each of these nodes as seeking equilibrium of a state of 0, every choice of a linear transformation is a prediction of the type, and so the result of this linear transformation at every moment accumulates prediction error as it seeks 0 prediction error. So it's kind of an interesting goal-driven process that works through group process. This is just a more in-depth description of the homeostat, basically constructed of 4 individual ultra-stable nodes. And the network as a whole creates an adaptive dynamical attractor set as a self-consistent reinforcing self-model. Ultra-stability powers its race of stable state space exploration through like the law of requisite variety, and can be seen as a network of reciprocal constraints. This is just an interesting letter from Alan Turing to Ashby back when they were members of the Ratio Club, and Ashby was getting some notoriety. Turing basically disagreed with Ashby's approach, and this letter here, he suggests that Ashby simply simulate his homeostat in his Turing machine. And while true, I think this Ashby was a bit taken aback by this because it kind of misses the point. At the time, the debate was all about analog versus digital computation, and what was useful to the war effort was most critical. But there was a bit of a conflation here, I think, in terms of what Ashby was trying to create, which was something more along the lines of universal adaptation or universal cognition, maybe, versus Turing's universal computation. I feel like this conflation of issues still haunts us today with deep learning and whether or not they're intelligent. So how do you build them? So essentially, I took Turing's advice and simulated it. In particular, 20 years ago, I was part of the Spectrumware project, which kind of pioneered software radio, which is now part of called Genia Radio. And so I kind of stole methodologies from this approach, where I created the homeostat as a digital simulation of a continuous analog system or device. And so that's kind of the approach I took. I started by poring through Ashby's technical journals, and experimented with different implementations and approaches of his direct analog machine. Once this was functional, it was simple enough to abstract down to very simple kind of minimal process. Once it's functional, you can start taking pieces out and see what breaks it and what doesn't. And eventually this effectively simplified down to a dynamical attractor definition for ultrastability that could be connected into arbitrary network topologies. And the network as a whole can be kind of seen as a self-model. Each node is trying to predict its neighbor as it seeks equilibrium. And the local ultrastability tunes a node's local connections and the resulting positive and negative feedback loops that it is personally a part of. And ultrastability tunes these as a group of these overlapping feedback loops such that they reach an homeostatic equilibrium. And that means that the local accumulated prediction error drops to zero, as well as the output from each node. And these overlapping loops become self-reinforcing and self-repairing. And it's this final self-predicting set of loops that maintains a self-model. At homeostatic equilibrium, this model converges and considered self-consistent. It is composed of these homeostatic feedback loops that maintain the network at a critical state, meaning that the network is highly sensitive to prediction error. I mean, the smallest prediction error can trigger global structural changes amongst these feedback loops. And this process can also be seen as synchronization, which I can talk about a bit later. So let me show a quick demo. I'm going to skip the original homeostat here, and I'm going to show a quick demonstration of what this actually looks like for a 20-node homeostat. It takes a bit longer, and it's a bit more demonstrative. So let me switch briefly here and apologize for the delay while I get this up. Cool. All right. So let me just describe what you're seeing here. You're seeing 20 single-dimensional graphs. This is the accumulated local prediction error at each node of the 20-node homeostat. You can also think of this as one 20-dimensional dynamical attractor or 20 single-dimensional dynamical attractors. These are also you consider these as phase space graphs for each of the nodes. So what you're seeing here is I have it paused. I'm going to move it along slowly. This is slowed down on purpose. And what you'll see is they start off very chaotically. And what happened is a couple nodes will start stabilizing, then more will start stabilizing, and then eventually the entire network will converge to zero prediction error. Now, this is unconnected to an environment, so it's just predicting itself. One thing I like to do here, and I don't know how many people else are going to find this interesting, I want to show a little in-depth look at what this final convergence and collapse to zero looks like. So what I'm going to do is I'm going to change this to auto-scaling the graphs, meaning that as it goes to zero, you'll see the graph ranges drop. And what you should see is usually there's a pattern forms amongst the output nodes that is kind of consistent with every drop. What you'll see is that it's kind of hard to see with 20 nodes, especially. I've gone a little too far. We're already at E-20 here. But what you're seeing is you're seeing the 20-dimensional drop to zero, and there's kind of like a cyclical pattern to this. And every time it goes through this pattern, it drops down another order of magnitude. And this will go all the way down to the floating point error of my computer, which is about -46, I believe. And then it basically fails to function at that point because it can't tell the difference. Floating point error, it can no longer function. So, and the whole thing kind of falls apart there. But that kind of shows you a bit about the process. Let me go quickly back to the slides. So yeah, that just kind of showed you a slowed down version of the 20-dimensional homeostat. And I wanted to show the 20-dimensional because it happens a lot slower and it's a little easier to see what's going on. With 4 nodes, it's almost instantaneous and it's hard to see the progression. Okay. So that seems like a lot of work for a model that doesn't really do anything and isn't connected to environment. So, we have this model that can adapt its internal structure to reach homeostatic equilibrium through kind of a self-synchronization process. How do we use this to drive behavior? And, this next step took me a few years, even though it's kind of conceptually simple, but don't worry, it'll get complex really quickly. The short version is sensors and motors kind of define how the agent is embedded into its environment, and the network topology defines the adaptive capacity of the homeostatic agent's model. Sensor definitions provide a mechanism to influence the behavior of the system by providing priors in the form of preferred environmental states. These act as kind of like Thiele dynamic priors, externally defined dynamic set points for the homeostatic adaptation. The motor definitions provide critical affordances for modifying the environment that provides the basis for future sensory predictions. The preferred states of the sensors become the preferred outcomes of the motors, and the model's behavior is biased as desired. This is probably, most people on this Active Inference Symposium are probably familiar with this idea. This slide is put together for the benefit of people who are kind of familiar with traditional deep learning and neural network approaches, to contrast how these networks function differently, because it's a bit hard for people to get their head around. The first is probably the most obvious, is there's no backpropagation here, only ultra stability, which is kind of a local rule. This leads to huge sample efficiency, and the learning is very structured, meaning you don't have to diffuse learning across thousands or millions of parameters. You only have to model the part of the you only have to update the part of the model that is mispredicting, or is part of a misprediction. The other thing to notice is that this is not atemporal. Most neural networks and like deep learning networks are kind of disembodied atemporal processes. This is very much a temporal process. Signals take time to move from one node to another, which makes it inherently, the whole thing, very temporal. The resulting temporal relationships are important, actually. Spatial relationships of sensors and motors end up getting encoded into relative temporal relationships within the sensory signals, and also vice versa. Signal timings of the propagating signals within the network can translate into different physical spatial relationships amongst the output motors, for example, or the input sensors. So there's a relationship between temporal location, relative timing of signals, and the spatial location of sensors and motors and the physical embodied agent. Different, and just to kind of push on that a little farther, the different regions within this larger homeostatic network will then be sensitive to different sets of motors, sets of sensors, based on their physical relative location. And by contrast, deep learning, deep reinforcement learning, for example, is an attempt at adding temporality to an otherwise atemporal static deep learning models. The other way to compare these two is, deep learning models are generally trying to be universal function approximaters, where this is much more generative and inherently temporal. The learning is very, very different. Just to expand a bit more on the topics from the previous slide, the network diagram here on the right is very oversimplified network, and it's just meant to visually explain how to think about some of these networks. There's no forward or backward, no front, back, top, bottom, only kind of relative location from other nodes and from sensors and motors, perhaps more relevantly. And it is common for people to look at the learning process as a sequential flow of processing, like sensing, perceiving, then acting, or planning, then acting. And instead, you have to kind of think of this as all happening at the same time, merging together as kind of one whole perceptual motor system, not a traditional sandwich model. Time simply advances, and we simulate the analog systems as signals propagate across the network. And so, you don't get input from the sensors, calculate the network, and get output from the motors. You send the input to the sensors, you get output from the motors and those motor actions are basically based on the generative model's prediction of what it should be doing already before having it even sensed the world. So what's interesting here from the model point of view in terms of how this homeostasis works is the network's homeostatic feedback loops come to be dependent on the expected sensory signals, meaning that the sensory signals become entrained in the homeostatic self-maintenance processes, which kind of naturally makes it grounded in the embodied experience. This homeostatic self-maintenance process is composed of the environmental signals themselves as part of its predictions and expectations. Expectations and predictions for the consequences of motor actions are embedded in the signals sent it to the sensors from deeper in the network, like on the right here, and they're sent to the sensors where expectation meets reality and prediction errors cascade backwards and modify the internal structure of the model as part of its model update. These and then motor actions are accompanied by these parallel sensory prediction signals that flow from the deeper in the network. The actions taken at any moment are not based on the latest input, but based on predictions driven from deeper in the network, from the same places that the sensory expectations are sent from. This may be familiar to those who are familiar with predictive processing or perceptual control theory. And the idea here is that where the sensors and motors meet the network, the network itself is trying to make those local prediction errors zero, meaning it's trying to anticipate the actual sensory experience through kind of inverse modeling. So another just kind of quick look at how to look at this homeostatic process is through synchronization. This process can be seen as generating an adaptive synchronization manifold between an agent and an environment around minimization of prediction error. This is kind of looking at synchronization as prediction. When two systems are synchronized, they can be thought of as predicting each other, anticipating the other's motions. And individual nodes using ultrastability are using ultrastability to learn how to predict their neighbors. And when at equilibrium, these nodes are kind of synchronized through these feedback loops. And this synchronization spreads from individual nodes to whole network synchronization, and ultimately out from the motors and back in through the sensors in a synchronization manifold between the agent and environment. To say it another way, the overlapping feedback loops interact and synchronize with each other as part of this homeostatic self-maintenance. And as these feedback loops extend from motors through the environment to the sensors, the model gains the ability to anticipate the consequences of its own actions. And the capacity to synchronize internal states with something in the external world, the synchronization means that internal states will come to resemble one will come to resemble the internal states of the other. This is kind of along the lines of the good regulator theorem. When at this synchronized homeostatic state, it's also in this critical state. I mentioned this earlier, where it's stable, but it's sensitive to local prediction error. So the meaning that the model, this critical state is maintained as long as local prediction error is maintained within a certain threshold. But otherwise, the smallest prediction error can trigger global kind of structural changes within these feedback loops in order to better predict the future. In order to maintain a synchronization, the network must be able to converge to equilibrium faster than the environment can destabilize it. And so there's, there's network update rates where we have to maintain, this kind of fast movement. And this kind of is in line with the law of requisite variety, where we have to make sure that we can explore state spaces faster than the environment we're attempting to control. And as long as the homeostatic network can establish these stable feedback loops faster than this synchronization manifold will be maintained. And synchronization is kind of an interesting thing, especially in the context of robotic control, because once kind of two elements are synchronized, let's say you have a subnetwork that's synchronized, then two nodes that are not directly connected can end up coordinating without any kind of communication between the two because they've been previously synchronized. Their behavior will end up being correlated as well. And in case it's interesting to think about, what is the structure of these kind of feedback loops and this, generative model. And the way I like to think about it is a dynamic hierarchy, meaning, a hierarchy is kind of like a top-down construction, but a dynamic hierarchy is more like a bottom-up construction where the parents are composed of the children, and dynamic in that as the children change their own self-definitions, the parents are likewise changed. So it's kind of constantly shifting and changing over time as the children redefine themselves. And this structure is very useful as a generative model, as allows a small number of individuals to kind of reshape the hierarchy very quickly as it's part of an ongoing dynamic process. Cool. So I'll switch over and do some quick kind of demonstrations showing how this ends up, why would you actually want to do this? Why would you actually want to do this, especially in the context of robotics? So the first thing I'm going to show is, let me just share here quickly. This is the demo I put together a couple years ago. Actually, let me shrink the screen a little bit so it's not quite so much to share. This was put together a couple years ago to kind of demonstrate, why would you do robotics like this? What is the point? And what does robustness mean, and what does adaptivity mean in the context of robotics? So hopefully you can see now my screen. This is just a simple modification of an OpenAI gem called Reacher, and it's been modified to add a single texture joint here, and the reasons will be obvious here in a minute. But this is just a simple task. It's the model has to get its end effector to the target position, and this is using these homeostatic models here. But here's what's interesting I can do, and this model hasn't seen this situation yet. I can disable the outer motor, for example, and it will basically on the fly figure out how to achieve the goal, just by updating its internal model and saying, oh, this motor doesn't work anymore. Let me modify my model of the world. I can turn that back on, and he'll start using it immediately, or it will start using it immediately. I can do the same with the internal motor. I can turn that off. And so, oops, I did not turn it off. There we go. Now it's off. So, and it just kind of figures out, oh, okay, the inner motor I no longer have access to. Let me update my model, and I can again turn that back on, and it'll start using it again. So this was just kind of a simple demonstration I made a couple years ago to show why you would want to do robotics this way, in that you can kind of get this real-time adaptation to unexpected situations due to the generative model that's constructed this way. Now, let me just scoot forward a little bit to more recent work. And hopefully the frame rate won't be too bad over Zoom. Let me just shrink the window a little bit in hopes that helps. Okay, let me share this. The frame rate feels a little rough over Zoom here. But this is all just running locally on my machine. So this is something a little more recent, a little more complicated. We made the goal a little bit more complex, and we've used a full 6 degree of freedom arm here from this is actually a fetch robot mobile arm, but something a little more realistic than like a toy problem. And I'm just periodically here retargeting the desired angle for this valve. And so this is just a robot that turns valves. And what I've done is that I can periodically change the set point for its, how it sees the world. Basically, you define goals by, defining preferred states of the world, and then the homeostatic model basically figures out how to control the robot to affect the state of the world that it wants. I'm hoping here every 30 seconds it will randomize the valve shape. The square one here is the simplest one. But let me add some random motion and random orientation. The model has not seen this before either, so it just kind of learns on the fly how to deal with this kind of moving shape as I do it. I can also do the sinusoidal motion here, so imagine it's on a floating platform where the rotation and the position are kind of moving through space. Here we go. Now we got something more interesting. So now we have it still moving through space. It's a circular valve here, something a little harder to turn. And what I'm going to do is I'm going to make it very slippery. So imagine I've just poured oil all over it. So now it's having to deal with a really, really slippery valve here that it has to turn, and it still manages to do it, even though it's really hard. But you can get the idea here is, if you do the generative model in this kind of sample efficient way, you can kind of get natural, adaptation to whatever it's kind of experiencing in the moment here. So I think this is maybe I'll do the random motion again. Maybe that's interesting. But yeah, there's all sorts of stuff you can kind of throw at this and it'll kind of deal with it. Apologize for the frame rate. I'm going to blame Zoom for that. Cool. All right, good. I don't think I have too much left, but next steps are basically improving automation and tools. I'm working. My startup is basically developing this for real world use in adaptive situations where you need fine motor control and kind of dexterous object manipulation in uncertain environments. It's on the technical side. We're looking at scaling up goal specifications and topologies, which are related, as well as deeper temporal horizons in both directions, planning and ahead and recall. But yeah. That's about all I had for today, and I look forward to the questions during the roundtable in a little bit. If anybody has questions now, we can talk to it as well. I went a little fast. I apologize. I'm a fast talker.
It was great. Just maybe one preliminary question. What settings do you see these kinds of implementations occurring in first? And then the other question in order, or if it's your preference, is how do you see the homeostatic network related to the analytical first principles foundations of active inference as we know it today?
Yeah, no, those are really good questions, and I didn't talk much about active inference because I figured everybody else had kind of done it pretty thoroughly. The use cases, your first question, use cases we're looking at are things that are just beyond the ability of current robotics. The idea here is this software could be put on, any old robot and kind of provide, adaptive capabilities for certain things. We're pretty open-ended in terms of what we're looking at in terms of use cases. Right now, our current use cases are in like energy and manufacturing, particularly. There's a fair amount of stuff that still has to be done by humans that could be pretty easily moved into robots if they had, a little bit more capability. And then in terms of how does the homeostatic networks kind of fit into the active inference framework in general, and I kind of touched on it a little bit in terms of how these ultra stable nodes work in the framework of homeostasis. If you kind of think of homeostasis as the network trying to seek, global equilibrium, what this means from the ultra stable nodes point of view, it means that its local output state is zero, and that local output state is the result of an accumulation process of this linear transformation. So the idea here is this ultra stable node, what it's doing is it's doing a search. It's doing a search through what are the right linear transformations that make my local state go to zero. And so in that context, you can kind of think of every time the ultra stable node updates its local linear transformations, this is updating its local model of the world and making a new guess about how the world works, and whether or not that's useful for the purpose of global prediction, it depends on whether or not it makes that local value go to zero. So there's a lot of threads here in terms of expectations and prediction error flowing through the network. But it's a much more distributed process. It's much less clear, what each node is what part of the model each node is taking place, because each node in the network, when it's changing its linear transformation, what it's actually doing is slightly redefining all of the feedback loops in all of the subnetworks in the network it's in, all of the loops that flow through that node, it's making a small change to. So each node in a certain way then has effect on all of the other networks that are connected through its feedback loops, and all those other nodes also have impact on its signals that are flowing through it. And this is this reciprocal process that kind of builds this generative model. I'm not sure if that's particularly helpful.
Yeah, that's great. If I could make one more comment and question, and then we'll bring Adam Safron on in just a minute or two. The letter that you showed was quite interesting, and I got the sense of this like multi-generational titanic clash between what you described as infinite computation in the discrete setting with the Turing tape, and then infinite adaptation in the continuous setting with the generalized cybernetics. And so I think that's a very fascinating framing, because what do people say about computers and continuous time systems? We're going to have to discretize. And so the implementation is stepwise, and that's what allows us to actually implement it on hard drives and CPUs and so on with the von Neumann architecture. But then also in the background, or even the water that we swim in, is this continuous time, the real-time unfolding of perception, cognition, action outside the sandwich model, outside of the discrete time.
Yeah, I'm really glad you picked up on that. I wish I was more qualified to speak on such topics. I'm a computer scientist, so I don't want to speak too far outside my field. But yeah, I think you hit the nail on the head of my gut instinct on it.
All right, we'll take just a short break and then come right back with Adam Safron. All right, welcome back, everyone. We are continuing on with Adam Safron, Generalized, Simultaneous, Localization, and Mapping, GSLAM, as a unification framework for natural and artificial intelligences. So, Adam, thanks a lot for joining, and please take it away.
Thank you, Daniel. So, hello, everyone. I'm Adam Safron. I am a research fellow at the Johns Hopkins University School of Medicine at their Center for Psychedelic and Consciousness Research. And today I will be discussing a grand unified theory. Another one. But before I do, as was previously mentioned, and as is probably of interest to people watching this, I recently co-organized a special issue of Frontiers in Neurorobotics with Ines Hipolito and Andy Clark. Most of the submissions are already in for you to read, and that will be closing up soon. There's also another special issue that I am co-organizing with other active inferencers and Fristonians for Royal Society Interface Focus on the subject of symmetries in mind and life broadly construed, ranging from symmetry breaking in dynamical systems to a gauge theoretic formulation of the free energy principle. This is actively soliciting contributions, and so please contact me if you have anything along those lines. So in this work and throughout all of it, my journey, I've been trying to understand the bases of autonomy in biological and artificial systems. Do we have free will? How does that work? Could we build autonomous agents that work like we do and have our capacities? These are the kinds of questions that have motivated me. Towards this end, I have been working on some fairly ambitious projects, such as a theory of consciousness that tries to bring together various theories within the free energy principle and active inference framework, and also models of free will in terms of the micromechanics of agency. Across all of this work, I take what I've called a Marian neurophenomenological approach, or Anil Seth calls it computational neurophenomenology, which I think is a better name. And roughly the idea is you take the core aspects of experience seriously as fundamental things to explain, and then you cross-reference this with a multi-level functionalist handling, or a Marian handling, where you can simultaneously analyze a system on computational or functional levels, what the system, what the different aspects are for, their adaptive significance, what the function they're serving. This algorithmic level, the abstract way, the specific programs and operations by which this is achieved, and the implementational level, or the physical realization of these. And so the idea is you take this multi-stack understanding of cognitive systems, and you cross-reference this with phenomenology, taking experience seriously. And this is my general approach. And active inference, with its associated process theories, basically checks boxes across all those levels. You have the free energy principle, you have active inference, and you have predictive coding. And these various claims of different degrees of specificity really help to flesh out this mutually constraining multi-level account of cognition. But more recently, I have been collaborating with roboticists. And here are two particularly excellent biobots, Tim Verbelen and Ozan Katal. And along these journeys, we encountered each other, and there's increasing interest in machine learning and artificial intelligence and things like artificial consciousness. You'll have people like Bengio talking about system to cognition, and more recently, even Lacuna has been starting to take these things on with his JEPA architecture, talking about world models of different kinds and how they might serve the functions of artificial consciousness. But for my collaboration with Tim and Ozan, we've mostly been focused on the specific problem of navigation, specifically a problem known as simultaneous localization and mapping. Roughly the idea here is that where am I in space, and what kind of space is this? This is a fundamental question for any active inference system, any cybernetic system. But there's a kind of a problem here in that you're trying to map out the space and situate yourself in it in the same time, simultaneously. So, but to map out the space, it helps to know where you are in the space. But to know where you are in the space, it helps to have a good map of that space. And so there's various proposals for different ways of bootstrapping yourself to degrees of certainty of what kind of maps or models are adequate for situating you in the world in a particular location. And this is going to be important whether you're a robot navigating through the world or an animal foraging for value. You got to know where you are to know what to do. So more recently in this collaboration, which I've really found to be amazing because I'm in awe of roboticists and what they can do. It's kind of like that Feynman quote of what I cannot build, cannot build, I do not understand. Well, they live that. That's just what they do all day long. They're like introspecting, how do I work? They're going into theory, and then they're actually building a system in this back and forth iterative process. And so the collaboration here was looking at, what ways can biological systems, and specifically focusing on the hippocampal system, what ways can these inform navigation problems? In this more recent paper that I'm going to be focusing on more today, called Generalized, Simultaneous Localization and Mapping, or GSLAM, we're reversing the flow a bit. And the idea is more than cognitive neuroscience informing robotics, it's looking more to robotics to inform cognitive neuroscience, basically leveraging the precision they have with characterizing these problems and the way they're in touch with the ground truth of engineering and physical moving systems in the world. Using this to inform cognitive neuroscience. And specifically, the claim is that this SLAM problem is fundamental and that it may have structured a surprisingly, maybe shockingly broad range of cognitive processes. And that this might be a source of fundamental principles for understanding how high-level cognition was achieved, with high-level put in some scare quotes, but the idea is the things that humans seem to be, or animals seem to be, particularly capable of doing relative to artificial systems, and humans in some ways even more so, and the properties we want to recapitulate in artificial intelligence and machine learning. So some precedent for this came from work with RATSLAM, the seminal work by Milford, Wyeth, and Pracer. So in this, they look to the rat in its hippocampus and look at its wayfinding and navigation abilities, and try to basically reverse engineer these. There's a really excellent YouTube video that I'll post. I've watched it countless times, which just summarizes this process of building up RATSLAM from like these initial foundations of the ambition, and folding in more and more details, finding this isn't quite working, going back to the biology, going back to engineering, and then actually showing systems that do the same things as biological systems inspired by those systems. It's extremely compelling. It kind of like, every time I watch that video, I feel like I get something new. I wonder, are these the steps that nature took in evolving these systems? And I also kind of felt like, what have I been doing with my life all this time? Like, why didn't I find roboticists sooner and started talking to them? So I'm very grateful to be part of this symposium. Latent, and very grateful for Tim and Ozen. And so with their work with latent SLAM, what they're doing is they're tackling the SLAM problem using active inference. I'm not going to be able to go into all the details here, but some of this was discussed. There's parallels with some of the architectures that were discussed previously, and Tim touched on this. So you basically have an agent moving through the world. It has a variety of views of what it's expecting to see and poses. And this experience map is a trajectory of the agent through space and time. And then here would be a generative model description in the middle of this, where you have these conjunctions of poses and views, which are unfolding in this series of transitions, adaptively sculpted via your policies, but where there's this upper level, which is basically organizing this as spatiotemporal trajectories, situating you in some kind of map or graph of space. And this conjunction of pose and view, one of the places I found this to be compelling is that I've arrived at these as basically the primary modalities I focus on just from like looking at the systems neuroscience. But this happens to be the primary things that are focused on for helping a robot to move through the world. And pose and view, basically for neuroscience, I focus a lot on systems such as the precuneus, as potentially enabling something like a mind's eye, and the lateral parietal cortices as something like a lived body, and that these would couple very closely. And that would make some sense since your pose would inform your view and vice versa. But there's another detail you need for this to be an autonomous system, an adaptive agent, which is not just like where's my body and what am I seeing, but where am I in space and where do I want to go relative to the world and the various things that I believe are in the world. How do I pursue my goals in the world? And so enter the SLAM problem. But what's built with latent SLAM, this is a very impressive architecture. Some details are described below, which, all these things governed by a singular objective function where the agent is able to not just make its way through the world, but also it's this powerful self-supervised learning curriculum as you're moving between views and pose and landmarks, each one providing a source of predictions for the other, training up the other, helping you to get a grip on the world. In terms of SLAM, two of the things that, so this like broader notion of G-SLAM or generalized SLAM, that this would be a way of thinking of high-level cognition. I'm particularly interested in these two operations. One's called loop closure, and the other's graph relaxation / node duplication. I guess that's three. But the idea is, as Tim mentioned, when an agent finds itself in a situation where its pose and view are highly similar to what was previously encountered, this affords a potentially unique opportunity. You now think you know where you are in space. And so this is a really good opportunity to update your experience map. And so this coming back around, it's not just a good opportunity in terms of you have high confidence, but it creates a closed system. So you closed a loop. And so you basically have these different equilibrium points in this graph, which can be thought of as a map also, but they basically, because they're all chained together, these are sometimes modeled as like energetic spring systems, and they're all mutually informing and constraining one another. And so when you find yourself with a loop closure event where you're in this highly familiar state, you then take this as an opportunity to refine your map. And so you will do a very fine, if you're within a certain margin of error of a location, that if you think you really got it, you'll then take the overall map and relax, and you'll basically move around the various dependencies of different nodes in space, the different landmarks, to adjust them and have each one refine the other, inform the other. However, if you're past some threshold for similarity and it looks like you're close but not quite there, you're a little bit different, if you're surprised, then you'll duplicate a node and then you'll create a new landmark. And so now you'll have a new graph. And so this is basically a kind of structure learning. And there's a lot of work in Bayesian cognitive science on, and within active inference, a lot of open work, like how do we effectively do structure learning for handling complex domains? And I'm suggesting, and I think Tim and Osman hopefully would agree, especially because we're writing together, would be that this provides a principled basis for doing structure learning. What's interesting here, though, in this diagram that Tim made, is that as you're mapping out this warehouse here, if you set these thresholds for identifying a node differently, if your graph relaxation / node duplication thresholds are set differently, you get very different models or maps. You might get very different structures, or if you will, schemas or scripts. That's not the frame in terms of a SLAM problem, but the claim here is that basically the hippocampal supposed place fields provide a basis for structure representations, many of which have resemblances to the kinds of things that were hoped for in like good old-fashioned cognitive science and in neurosymbolic AI. And so and part of what's hoped for is some of the aspects of potentially uniquely human cognition, high-level cognition, require some sort of representational scheme. But if you set these but if this is the mean by which you arrive at representations, and if these parameters set differently could give you wildly different representations, these would have very different impacts on the kinds of minds you might have, potentially including even things like cognitive spectrums if you were to apply this to a biological domain. And so there's some notion that, for instance, you could even potentially think of these parameters for the hippocampal system which are maybe evolutionarily were originally laid down as parameters for a SLAM problem, for an animal finding itself in the world, but where they continue to operate in terms of the mechanisms of hippocampal and entorhinal plasticity, that these, if they're parameterized differently in different people, could give you very different kinds of minds. And this potentially has very, the significance of this might be difficult to overstate in terms of characterizing human difference. These might be some of the most important variables you could look at for saying how people differ in the way they relate to knowledge in the world. And not just, so this would have clinical consequences, basic science consequences, maybe even helping to explain some of uniquely human cognition, the kinds of things that help to get symbolic reasoning and like cumulative culture off the ground. There's other proposals that are kind of similar to this Mad Dog navigation perspective or SLAM perspective. Jeff Hawkins out of Numenta has a proposal he calls 1,000 brains theory. Technically, it should be called something more like 100,000 brains theory, where the idea is that there's a common cortical algorithm carried out by every single cortical column of doing this object modeling and navigation of the kind described for the hippocampal and entorhinal system. I find aspects of this to be compelling, but also very mixed feelings, and I can talk about that later with anyone who's interested. There's another recent proposal in this spirit by Chris Fields and Michael Levin, where they're basically characterizing morphogenesis as cells engaging in a kind of wayfinding and navigation process of where they ought to be in this synchronization manifold of the phenotype. And so they're all finding their place, singing, as Karl might say, like singing from the common hymn sheet, knowing where they are, but as they're synchronizing, they're moving around to find where they are, this unfolding geometric melody that eventually becomes the phenotype of the organism. But the idea is that this intelligence of wayfinding at the cellular level, many of these mechanisms may have been repurposed and recycled and deployed differently for overt navigation, and that this is a frame for intelligence more generally. I find this to be extremely compelling. Although what I'm doing with this work is I'm focusing more on the hippocampal and entorhinal system as a source of specific adaptations with specific properties and a major transition in evolution, potentially also with some connection to things like Ginsburg and Jablonka's major transition markers and unlimited associative learning. They have a lot of emphasis on the hippocampal system and its homologs. There's very interesting work that I'm only beginning to look into in the insects with the central complex and the mushroom bodies and the way they handle navigation. I think cross-referencing the mammalian version and the insect version would be really invaluable, and that's a major to-do that I'm hoping Daniel will help me with. So some other precedents would be in terms of this idea of generalized navigation, that this would be a powerful frame for understanding cognition. Comes from some older work with Hasabius and McGuire. They found, interestingly, that hippocampal patients, not only are they impaired in episodic memory, but they have trouble with episodic imaginings of counterfactuals of novel situations. And so they talked about this construction system of this brain, this core system for memory and imagining, allowing for various forms of sophisticated modeling and creative cognition. And this seems to have been part of what basically gave Demis the confidence to go and found DeepMind. And this is still a core aspect of what they're doing there. And the race is on for reverse engineering the system, and the race is heating up. And some really excellent work would come from Timothy Barron's group. I believe he's still at UCL. They're showing, like, for instance, there's an architecture called the Tolman-Eichenbaum machine, which I strongly recommend checking out. That's active inference compliant and as a realization of the functioning of the hippocampal system. They don't focus as much on navigation, although it can be used for that, and that's part of it. That I'll come back in a second for the differences here, but in this work, one thing of note is, so they're showing basically people categorizing these stimuli, where you have these birds with different length necks, and there's a kind of morphospace in terms of characterizing the features and their various dimensions. And basically, they're showing hippocampal / entorhinal-like representations, grid-like representations, being involved in helping to map out this feature space. And so this is one example that's very commonly cited of spatialized cognition, of something that might not seem clearly spatial. But then the idea with GSLAM would be, once we've spatialized it, then to what degree in our sense making is it actually a kind of navigation through the space? And so this process of spatializing and navigating through the space simultaneously I would call that a SLAM problem. And I think a lot of cognition can be fruitfully framed in this way. And I'm going to go a little further. So here's the Tolman-Eichenbaum machine, and he's showing like different, I don't know, is his face covered by the thing? I can't tell. Well, there he is. Yeah, so his work is unbelievable, his group. And, but, you know, different things like relations among people within hierarchical tree structures of their relations, doing things like transitive inference of one property related to another and a set of dependencies, but basically using the hippocampal system's properties to navigate and manipulate these spatialized representations. There's other work from DeepMind. There's this other talk highly recommended by Stachenfeld et al. At the main conference. It's unbelievable talk, talking about the recent work from DeepMind to reverse engineer the hippocampal systems, place cells, and the grid cells of the entorhinal system as allowing for a variety of properties. Some of, you know, very similar to Baron's work, and they collaborate together. But one thing that's interesting about this talk is she makes a point that this isn't just for tasks that are like physical space. This isn't necessarily spatial. I might challenge that a bit and say that we should basically always have a prior of looking for the spatial properties of any task domain and then wondering to what degree can we frame this as a SLAM problem. And I think there's maybe two reasons for doing this. One, maybe three. One is that basically putting things into a common framework helps to you to draw analogies across seemingly heterogeneous domains, and this can be a source of insight in terms of a common representational framework for sense making. Sense making gives you an ability to have creative combinations from seemingly different domains. So, but the other reason is the hippocampal system, like this, was specifically probably what it was selected for. This is a mapping system for a animal foraging through value through various spaces. And this isn't just evolutionary, but this is also developmentally and ongoing. This is an ongoing problem. We have not transcended this. We are still in space. We still constantly have to move through space and situate ourselves through spaces, physical spaces, and also conceptual spaces. So that's part of the reason I'm really emphasizing the SLAM framing, because the hippocampal system will never lose this job description. And the idea is that understanding the ways in which it's parameterized, specific operationalizations, I don't think that's a word, it's essential to keep in mind this ecological significance. And so this is all within the spirit of, I guess, a broader view in cognitive science called ecological rationality, which is go back to the origins and try to understand. It's Tinbergen's quote, "Nothing in biology makes sense except under the light of evolution." Take that very seriously and run with it. One other thing that's, so along these lines, one thing I think you get is connections. One thing a GSLAM perspective gets you is connections to foraging theory. And so, you know, if you're thinking of an animal going through the world, trying to extract value, resources are often patchy. And so as you're moving through the world, you might be, you know, balancing exploration and exploitation with respect to, if you find a patch, might be good to exploit that for a bit if it's particularly juicy. But then as that patch dries up, maybe it's time to go explore. And then you want to adaptively move between phases of exploration, exploitation, staying longer in some places, and then moving to other places. And so these jumps to other places, like when a patch starts to dry up, and these are sometimes known as levee flights. And this is playing actually into some of my work in psychedelics, and that informed by some really intriguing suggestions from Matt Schein's group. The idea is that one of the mechanisms impacted by psychedelics might be potentially facilitating these kinds of levee flights, where you can think of more creative cognition as involving more exploration, more broad associations. And there's and foraging theory, you know, it's extremely rich and well developed. There's all sorts of different modes of foraging that could be thought of as different modes of cognition. There's specific hypotheses and connections to formalisms like the marginal value theorem. So you would have like a hypothesis like, you know, when do you leave? Well, in the marginal value theorem, the idea is you leave a patch, or when do you go and try to find a new? You leave a patch, when your current estimated value drops below what you think the average rate of return should be. So this then, gives you basically, like, you can now characterize people, where are they relative to these different normative models. And this idea maybe has an even older vintage, or maybe newer relative to evolution, but old relative to discourses in terms of the art of memory and the method of loci. Memory, especially before we wrote everything down, or when writing things down was expensive, and even now, to have something in your mind where it could be at hand, where you can retrieve it, to have like a well-curated set of knowledge, it's essential. And so one of the best tricks that were discovered is you actively, intentionally spatialize your knowledge. You actually create a physical place that you visualize, and you move through it. And at each point in this space, you've placed different things you want to remember. And part of the reason this likely works so well, like almost certainly, is this is, the core of memory in the hippocampal system is actually involving a process of, it is a spatial mapper. That's something I would argue. There's connection to some other work in cognitive science I'm not going to get into right now, but like multidimensional scaling, where you understand potentially complex domains by mapping them onto a simpler and potentially more cognitively navigable space. And then, I'm not going to get into this right now, but actually I will. So real quick aside is with respect to multidimensional scaling, one of the early things that got people excited about it was its potential use for analogical reasoning, or establishing similarities between domains. It's a very important thing to know, like, how similar is something relative to something else? Like, should these things be placed in the same category? Or, and one way of doing this was saying, what is the distance in this, when you do multidimensional scaling and you place something in a feature space, what is the distance between different things? And the further apart, the less similar they are. But there are other models of analogical reasoning, and there's another race on to try to figure out how we do analogical reasoning. And so some of these proposals, they would go on beyond something like multidimensional scaling, but they would involve specific structure representations. But then we have a question, well, what's the ontological status of such things? Do they actually exist in the mind in some way? Do we actually have representations? Or maybe these things are more like they're virtualized or inactively realized or implicitly. I suspect many of the kinds of structures, described in good old-fashioned cognitive science might not be biologically plausible, but they might be surprisingly biologically plausible if you actually have a system capable of adaptively constructing graphs based on your ability to extract value from these graphs and situate things relative to other things. And so it's possible that some of analogical reasoning and even causal reasoning could be unlocked by having a good means of creating structured representations. And one of the things the hippocampal system might seem to be able to do is create these graphs where the different place cells of the hippocampus can be thought of as nodes. And so if you duplicate a node, you are now basically doing structure learning. You're complexifying this representation. So this comes into my work in other ways, such as models of goal-oriented behavior. I'm not going to get into too many details right now, but here would be the hippocampal system, and you see, based on work of people like Reddish, and also like Sam Gershman has a successor representation model. But basically, you'll see these predictive. The hippocampus is a predictive map, where what's being predicted is where you'll see these sweeps of activity that will proceed in front of the animal and then which will predict what choice it will do, what arm of a maze it might go to. And so the idea is that the hippocampal system is the top of the cortical hierarchy, and that any prediction errors that are not handled elsewhere end up get temporarily stored in this volatile memory system, but which is also encoding these trajectories or these series of equilibrium points of state transitions. And that basically you have prediction errors that are not handled elsewhere, make their way there, get temporarily stored, and you can have what's sometimes called a semantic pointer architecture, where basically as you're stepping through these various equilibrium points, you can then unpack this as estimates of system and world in terms of operative policies and actions and what you expect at different points along these different trajectories. And so here I'm focusing on moving through a physical space, in this case making T, but this is, I would argue, this is also part of what we do when we navigate conceptual spaces, that we are deciding what branches do we go down, to what degree, where will we find what kinds of value, and that this is a similar operation using similar procedures from common neural processes. More recently, I've been trying to extend this to models of volition, including free will. And let's see. I don't, so, Daniel, how much time do I have left? I'm sorry. 10 minutes? Okay, great. So this is less, I guess, explicitly slam framed, but still it's a hippocampus at the center of it. And so here, I'm trying to, this is a recent piece, it's in preprint form, which I'd love feedback on. But basically, the idea is that the present moment of experience has a thickness to it. This is sometimes called the specious present or the remembered present. And that it seems to vary that the minimal thickness of a moment of sense making seems to be about 1/3 of a second, and the upper bound seems to be about 3 seconds. And that this seems to correspond to an epic, so you basically can, so the hippocampal system can, whenever you enter like a room, it'll tile that domain with a certain degree of granularity. It'll create these hexagonal tilings of that space. And then within there, that's where you'll have these different attractors, these different trajectories play out, orchestrating the rest of the brain in terms of its dynamics to pursue these various goals. And so the runway you have to work with in terms of the thickness of the different rollouts for sophisticated inference would depend on partially the shelf life of this set of attractors before you have to refresh them in some way, either set down an entirely new set or try to recreate the old one or prevent the remapping. And this would be related to some of what was just described with air dynamics in terms of how good of a grip do I have. So let's say you have like a poor grip on what's happening and your prediction error is going up. This is not a good situation for you. That might be a good opportunity to stop, halt, and catch fire, retile space, get a new set of operative policies for sophisticated inference. And so, so here what I'm trying to do is show that different levels of agonism of these serotonergic receptors involved with psychedelics, 5-HT2A receptors, are influencing the stability of these sets of attractors and the vividness with which you are doing these imaginings and of rollouts of actions into the future. And here it seems that what you could potentially do is describe some of a dose response curve for something like psychedelics, where as the dose increases, the extent of the rollouts become greater. You've stabilized them, and imagination can become more vivid and can influence your policy selection more because you have more confidence in what you're seeing. And so sophisticated inference, your imaginings are contributing more to your ongoing overt action selection up to a point. But then, and so this would be, and so this, but then at a certain point, the idea is you keep dosing the animal or maybe the robot, and it enters more of a creative dreamlike regime where it starts to lose coherence, and you see the extent of these rollouts of policy selection decreasing. Things are becoming more vivid, but less coherent. And sometimes you're getting, and this itself could occasion error and potentially regripping in this model. And so the idea is that this would be a cognitive spectrum potentially, in addition to explaining some of the neurophenomenology of things like psychedelics. This could potentially explain some cognitive spectrums, whether we're talking about maturation or aging or waking up, when you first wake up to going to sleep, these different parameterizations of your mechanisms for sophisticated inference, helping to basically provide a neurophenomenological handling of human of what it's like to be a person and all the variations of it. And so I think that should be it for right now. And happy to talk about all this with anyone who's interested. Thank you.
Awesome. Thank you, Adam.
Hi, Daniel.
Hey, any
You're muted.
thank you very much. Any other notes you'd like to add?
Um, I think that's it for the moment.
Great. Hope that you consider anything and join us for the roundtable shortly. So thanks, and we'll be right back with the final presentation by J.F. Cloutier. All right, we are back. This will be the final presentation of this interval. This is J.F. Cloutier towards a symbolic implementation of active inference for Lego robots. So looking forward to hearing this and then seeing you on the roundtable, JF.
I'm Jean-Francois, and I will talk about how I program Lego robots as active inference agents. This work contrasts with most robotic implementations of active inference, which are based on probabilistic inference. So I hope this will spark some interesting discussions. Well, first of all, I'm a software developer. I'm not a neuroscientist. In my spare time, well, I like to code models of cognition because I'm keenly interested in all matters of cognition and consciousness. And I run them on robots because the real world is hard. And I believe that writing code for robots is actually a very good way to test my understanding. And coding itself helps make abstract concepts tangible to me. So what do I want to accomplish? Well, I want my robots to learn autonomously while they conform to the principles of active inference. This is the current version of my robots. There are two earlier versions, and there's one in early development. And here we'll see my robots, to the left, Karl, to the right, Andy, driven by the interplay of generative models for hunger, danger avoidance, and wanderlust. Let's see them in action. They navigate a space. The sheet of paper on the floor represents food, and they are attracted by the scent of food simulated by an infrared beacon on a pedestal. So Karl is making a beeline to the food while Andy is having problem getting traction and bumping into the walls. Karl is cautiously approaching, but will get a little bit too close to the pedestal, and this will engage its danger avoidance, collision avoidance generative models. He backs out. Andy is observing all this, and he backs out as well. Karl is reapproaching the food. And this time we'll eat successfully. Andy has noticed that Karl was freaking out. And in sympathy, freaks out himself while Karl is eating. All right, so that was the robots as they are right now after 3 iterations of this project. So what does it take to implement an active inference agent? Well, there are 3 approaches. One, One could take the numerical approach, which basically puts the mathematics of active inference into code and runs that on robots. Another approach is to take a symbolic approach, where we have code functions that operate mostly on symbols, predicates, etc. Here we can see we have the symbols for hungry, very, danger, curiosity, etc. But that's not the only option. Take E. coli. E. coli is an active inference agent, and its implementation is biochemical. Well, I clearly didn't take that route. I went the symbolic route. Well, mostly because it's the familiar one to me, and it provides me with a better scaffolding for my intuitions and exploration. I also find that it handles complexity quite well. When I started this project in 2017, my first thoughts were to implement a society of mind. I'd come across this concept decades ago. It's a theory of mind put forward by Marvin Minsky 50 years ago. And at its core, it says that intelligent behavior emerges from a lot of simple actors that interact in simple ways. It so happens that I look at it as an architectural principle as well. So how does one implement a society of mind? To me, the answer is clear, is we use the actor model. The actor model is a model of concurrent computation that was introduced by Karl in 1973. According to this model of computation, we have independent actors, which are processes, concurrent processes, each one managing its own state. And the only way an actor can interact or influence another actor is by sending it messages. And once an actor receives a message, it will interpret that message, possibly modify its internal state, and as a consequence, fire messages to other actors. So building a society of mind using the actor model is quite a natural fit. I also happen to program in the Elixir language, and Elixir is a message-oriented multiprocess language, which is based on the actor model, so it's a perfect fit. So here we are, it's 2017. I own two Lego Mindstorms EV3 kits. They're wonderful robotics kits with a nice choice of sensors, mini motors, and a computer, the EV3 brick that controls them all. And I want to build a society of mind in Elixir on my EV3 robots. I'm in luck. There's a Linux distribution called EV3 Dev that allows me to run Elixir on the EV3 brick, so I'm all set. So that allowed me to start this project. And this project, as I said, has completed 3 iterations, and I'm starting a 4th one. And we'll look at each one in turn, reviewing the goals and also the issues uncovered. First iteration, 2017, version 1, a simple society of mind, as I call it. So I implement an ad hoc model of cognition. It's not something that I took from research. It's something I made up myself. It's homebrewed. And let's have a quick tour. So being a society of mind, it's populated with actors. And we have the detector actors, and their responsibilities are to interface with the sensors and to pull them periodically to generate percepts, which are events that are, like all other events that the actors will produce, are sent to the central nervous system actor, which is a dispatcher, which will then dispatch these events to other actors that are interested in them. There's a memory actor, and all events are sent to the memory as well to be stored for a certain amount of time and represent the past, if you want, to the agent. And the other actors are able to query this memory in order to make whatever decisions they need to make. One of the key actors are the perceptor actors. And what they do is they ingest events, percept events, originally from the detectors, and analyze them, maybe in the context of the past, and produce higher level percepts. For example, a perceptor might be digesting a distance percept from a detector, look at it and say, given prior distances, I'm getting closer to an obstacle, and in a higher level, and then produce that percept, and the higher level perceptor might say, I am getting closer to an obstacle, and I am currently close to it, so produce a percept that says collision imminent, and so forth and so on. Another important cognitive actor is the motivator, and the motivator is responsible for deciding what the robot needs, what the robot wants, and it expresses this need or this want as a motive event that is, again, centered in the central nervous system, dispatched, in this case, to the behavior actor, and the behavior actor then takes this motive and acts on it by emitting intent events that are listened to by the actuator actors, who translate these intents into actual commands and move the robot. One key point is that the motivators actually are compete with one another, so that the most important need of the robot is the one that's expressed. So, for example, getting to safety is more important than satisfying hunger. There's let's look a little bit into one of the types of actors, the behavior actors. And the behavior actor is actually quite complex. It does a lot of work. It's not a simple actor. It's implemented as a state machine. And with every state transition triggered by new percepts, intents are emitted. And so we can have a behavior actor which job is to direct the robot to the food. So it works. So let's see ND version 1. Moving about and trying to get the food, which in this case is the blue paper on the ground. So it tries to avoid collisions. It does not always succeed. Here it finds out it's stuck. Backs out. Goes around. Doing a better job at avoiding obstacles. And now makes a beeline to the food, having detected it. Approaches cautiously and feeds. All right. So this worked quite well, but there were issues with this version 1. I don't think it was visible in the video, but the robot was frequently overwhelmed by a constant flow of percepts. The perceptor, the detectors constantly feed percepts into the society of mind, and after a while, they kind of back up, and the robot starts reacting to old events. And one solution was to actually put the robot to sleep once in a while, paralyze it, let the events wash through the system, and then wake it up with a clean slate. So that was kind of a little bit awkward. And another issue was that, well, there's no learning going on. The robot doesn't get better with each run. And given the model, it wasn't clear to me where I could fit learning in there. So time for version 2. So I need to find a way to make my robots learn. And they also need to better focus and be able to have attention so they can avoid being overwhelmed with all these unneeded sensations. I also need more computing power, so I replaced the V3 brick by a Raspberry Pi 3. About the same time, I come across Andy Clark's book, Surfing Uncertainty, and I find that the predictive brain makes quite a lot of sense to me. I think it tells a really good story about learning and attention, so I decide to implement a predictive society of mind. This is my first crack at it. I won't go into the details. I do in a companion paper. Let's just say that there are actors for managing beliefs, validating them, making predictions, and taking action when to make these predictions come true. There's also an attention actor for turning detectors on and off as needed, and a focus actor for prioritizing belief validation. I do introduce some learning. The robot learns what actions correlate well with success, but that's about it. And there's the model does not feel quite right to me at this point, and they are bottleneck actors. For example, there's only one experience actor, there's only one attention actor, only one memory, of course, and only one focus. And in a society of mind, that just doesn't feel right. Yet, it works. And let's watch ND on its first run. It's ND version 2. Hasn't learned anything yet. So same scenario. So ND has detected the food, would like to move towards it, but doesn't know which actions validate beliefs best. It smells food, but still, it's just heading into the wall. So poor ND is being quite unproductive here in its quest for food. It's a little bit painful to watch. Let's stop. Now here's ND 30 runs later, and it's much more competent about matching beliefs and actions. Smells food and very competently makes a beeline to that food. Just. Here we go. Slowly approaching. Obviously a very different ND from the naive one. And there we go. Okay, so it worked, but there were issues with version 2. First, the model doesn't quite feel right to me. It just doesn't quite capture something. I didn't feel right about it. And there were bottleneck actors as well, which is not a good sign. And learning was limited to action selection. So time for version 3. I call this one a Society of Generative Models. So I go back to the Andy Clark's book and also read on the free energy principle. And it becomes clear to me that generative models are actually quite central. In fact, it's generative models all the way down. So I get to work on a new model. In this new model, I have very few kinds of actors. They're detector actors, as before, to interface with the sensors, actuator actors to interface with motor speakers and whatnot. And the only other kind of actor are the generative model actors, the GM actors. And there's quite a few of them, in this case here, 16. And they do the heavy lifting. They do the belief updating, the predicting, the raising of prediction errors, the selection of actions, and they are responsible for remembering their past states and actions. Each GM operates within its assigned scope. There's one for locating food, one for avoiding obstacles, one for detecting approach to obstacles, and so forth and so on. The GM actors have parent-child relationships. A parent GM sends predictions as events about what it expects its children GMs to believe, even what it itself believes, and these predictions flow downward, and prediction errors flow upward. If a child GM receives a prediction about what it's supposed to believe, or it's expected to believe, and it's not what it believes, and it sends back a prediction error up to its parents. Well, that means that a generative model's perceptions are, in fact, the uncontested predictions it makes, plus the prediction errors it receives. And the GM updates its beliefs based on these perceptions. And given what it believes, it may decide to take some actions and then raise intent events that reach the actuators, a little bit like before. The generative models are kind of grouped into different areas of concern. There's being, which is responsible for deciding whether we're in danger, we're hungry, or we're free. There are the danger GMs, which have to do with clearing obstacles, trying to stay in well-lit areas, avoiding collisions with the other robot and whatnot. Then there are hunger GMs that have to do with eating, seeking food, etc. There's the freedom GM, which I call the wanderlust GM, which basically says, well, I'm neither in danger nor hungry, so let me just roam around. And finally, there are these two ones here, which have to do with guessing the intent of the other robot and we'll go into more details with these two. So let's look more closely at the GM actor. Remember that a GM has parent GMs and child GMs, that predictions flow downward and prediction errors flow upwards. Let's look inside. A GM defines one or more conjectures. A conjecture is a potential belief. For example, whether I know where food is or whether I'm about to collide are two different conjectural beliefs. A belief may either be a goal, that's a belief we want to make true, like I'm eating, or an opinion, which is a belief that I want to validate, for example, that I am approaching food. A conjecture is typically activated when the GM receives a prediction about the conjectured belief, and a conjecture knows how to check its associated belief to see if it's valid. It knows how to make predictions given that belief, and how to decide what actions to take to either achieve or test the belief. A GM learns how well alternate courses of actions, policies correlate to achieving validating a belief. It also keeps track of which child GM it trusts more should they send competing prediction errors, so it does precision weighing. And each GM actor works in its own time. It's a concurrent process. And it does it operates one round at a time, and we'll see what a round means. And it remembers its past rounds, its past perceptions, the predictions it's received in the past, its past beliefs and actions. So now let's look at the life cycle of a GM actor. Well, as I said, a GM actor operates round after round after round. So what's a round? First, when a round is started, a GM carries over the perceptions and beliefs from the previous round. It doesn't start from scratch. And if it's in the midst of trying to achieve a goal belief, it may, as it starts its new round, activate conjectures for that action belief, and as a result, send predictions to child GMs. Once we're done starting, the round is active, and then the GM actor just sits there for maybe, 300 milliseconds, waiting for events. Events like predictions coming from above, from parents, that will then activate conjectures, trying to prove that the predicted belief is actually true. This will cause predictions to be sent to child GMs, and as a consequence, maybe prediction errors will come up, and the GM will update its perceptions. When the round is completed, either because we've heard from all the children or because time's up, the GM completes this current round. It updates precision weighing, keeps its trusted perceptions, updates its beliefs. As a result, may send prediction errors because the new beliefs conflict with predictions that it had received before. It updates its policies, and decides on a course of action, sends intents, and notifies that the round is completed, and we continue. So round after round after round. I mentioned that there were two very kind of more interesting GMs in the Society of Generative Models. These are these two GMs, and they represent my little foray into theory of mind. These GMs are dedicated to guessing what the other robot is doing. So each robot observes the other and detects patterns of movements and infer intentions from these patterns. There's only two kinds of intents that are inferred. One is that the other robot has detected food and is making a move towards the food, or that the other robot is in danger and is panicking. Now, how does a robot see the other robot? Well, in addition to the array of sensors I already had from previous version, I've added a new sensor, a 360 beacon seeker, and what this beacon seeker sees is the beacon on the back of the other robot. So each robot has a beacon on its back that broadcasts in a 360 radius circumference angle. It signifies here I am, here I am, here I am, and the other robot can detect how far the other robot is and at which relative orientation. So that, let's say one robot here, Karl, is making a beeline to the food. Andy has been observing this and seeing the pattern of movement, which is a very straight trajectory, infers that Karl has detected food and is homing in on it and may decide to follow Karl and get to the food as well. Another pattern of movements would be a chaotic pattern of movement. And let's say Karl had been backing away in panic from hitting the pedestal, and Andy was observing this and it noticed that this kind of chaotic pattern and inferred that Karl was in a panic and decided to get into panic as well, if you remember the video at the beginning of the presentation. So this is going well, but we all know debugging is hard. I find out also that debugging societies of mind on robots is very hard. In order to help myself, I develop a simulation environment. I think of it as simulated embodiment, which allows me to observe what goes on inside a given robot. It helps for debugging. It helps for experimentation. In the simulation world, my robots, virtual robots, live in a grid world. There are obstacles, the blue tiles. There are kind of darker areas that the robot tries to avoid, which are represented in the black and gray squares. And then there's the food, which is the green tiles here. As the robots navigate that space, by using their society of generative models, I can see where each robot is in terms of its state. First, I can see where it's located. I can see its orientation, what it's last said, what last action it executed, and I can see the state of its virtual sensors and virtual actuators. I can also peek inside the various generative models of a robot. Here I'm looking into the avoiding obstacle GM of Andy, and I can look at the state in the current round or in past rounds, and I can see which predictions came in, which conjectures are activated, what are the current perceptions, what beliefs that the robot hold at the time, and what actions it thinks are more likely to work, and what actions it is taking. Very, very helpful. But this moves really fast, and so I can actually slow down the simulation and even pause it, and then look inside the various generative models and see if what's happening is what I expected would happen. So great debugging tool and experimentation tool. So I'm quite happy with version 3. I think it aligns quite well with the active inference ontology. There are no bottleneck actors, but learning is still limited to selecting action policies. However, I think that the version 3 sets the stage very well for a new iteration, and this one has an ambitious learning agenda, and it's just getting started. So version 4, starting now, I call it active inferencing. So here's what I want to achieve. As the robot interacts with its environment and learns how to maintain it, I want for it to learn how to maintain its homeostasis by growing its own society of generative models. So instead of being given an a priori set of generative models, I want the robot to learn that set. Not only that, but I want each GM to learn its own capabilities. I want it to infer its logic programs that, when executed, will infer predictions from perceptions, will infer beliefs from also from its perceptions, and infer policies that will validate or invalidate its belief. So how does one do that? Well, there's a very, very interesting paper that I found, which is called Making Sense of Sensory Input, written by Richard Evans and all from DeepMind. And it answers the question of how do you learn a causal theory that explains a sequence of sensations. And once you've built that causal theory, you can then apply it to predict what the next round of sensations or perceptions will be, and thus make predictions about them. Just to read from the beginning of the paper, making sense involves constructing a symbolic causal theory that both explains the sensory sequence and also satisfies a set of unity conditions. Now, unity conditions are actually a set of constraints derived from Kant's philosophy that ensure that all the pieces of the theory form a coherent whole, semantically speaking. I won't go into the details, but it's quite fascinating. The paper goes on. Making sense of sensory input is a type of program synthesis, but it is unsupervised program synthesis. So the paper presents an apperception engine. This is the software that will generate, will infer causal theories from sensory data. It is, at its core, it's a code generator. What it does is it synthesizes logic programs that implement these causal theories. And when you run these logic programs, you can predict incoming sensations. So essentially, an apperception engine generates predictors. And the way it does that is it searches for predictor logic programs in a space of potential possible logic programs. It's a search problem, and the search space is extremely large, of course. So we need a way to constrain it. We need to apply strong inductive biases to restrict the search. That's where the unity conditions come in. So, in order to derive its own predictor, a GM will search for good predictors using apperception. So, given a prior round of perceptions, remember that the GM has a memory of each round, and in each round a set of simultaneous perceptions. Given that sequence, a GM will search a space of candidate predictors for a good one. What makes a predictor? Well, two things. First, there's a scope, and then there's rules. The scope is essentially the objects the rules will be about and the belief predicates that will be used in the rules. The rules, well, there's three kinds of rules. There's the static rules, which apply on a set of simultaneous perceptions, like at time n, and the rules validate and possibly also infer implied perceptions, missing perceptions. An example of a static rule might be if the robot is at distance 0 from an obstacle, it is also touching the obstacle. Then there are causal rules, and the causal rules essentially infer the perceptions at time n plus 1, given the perceptions at time n. They predict the next perceptions. An example of a causal rule would be if the robot is at distance x from an obstacle and the robot is approaching the obstacle, in the next round of perception, the distance of the robot to the obstacle should be smaller. And finally, there are conceptual rules, which are rules that kind of make the whole predictor hang together semantically. There are rules of mutual exclusion. For example, there can only be one distance between a robot and an obstacle. And rules of uniqueness, rule of uniqueness would be that there can only be one distance. Yes. Rule of uniqueness, there can only be one distance, for example, between two objects, and mutual exclusion might be a robot cannot both approach an obstacle and be touching it at the same time. So the apperception engine will kick in for a GM when the current predictor of the GM is no longer good enough for the job. Like we've produced a predictor, and now we have more rounds of perceptions, and the predictor is doing a really bad job at predicting the next perceptions. And then the apperception engine will kick in and try to produce a better predictor for that GM. So that happens for all the GMs. And once we have a good predictor, the GM, given the current set of perceptions, can infer the next set of perceptions, thus make predictions. So we talked about how a GM learns, but what about how it learns? How about learning the entire society of GMs? How does a robot form its society of GMs through interactions with the world? Well, this was going to be guided by a metacognition GM. That's something that's given. When the robot starts life, it has a basic set of detectors, set of actuators. That is a given. And it also has a metacognition GM. It's also a given. The metacognition GM, its role is to watch over and guide the evolution of a society of GMs. That's the action. For it to function, though, each GM must act as a cognitive sensor. It must produce sensations such as are prediction errors trending up or down? Do policies predictably impact my beliefs? Or, very importantly, within my purview, is the robot's homeostasis at risk? These are cognitive sensations that a GM will produce, will be listened to by the metacognition GM, and that will allow it to update its own beliefs about how well the society of GMs is doing. Does it have sufficient coverage? Is each GM capable enough? And based on that, may take corrective actions by creating new GMs. And possibly, if one GM is not doing very well, it's stuck in a rut, removing it and replacing it with another. So that's the role of the metacognition GM. So how can the robot tell whether it's doing better or worse than before, given what it has learned? Well, feelings. That's how. So a robot will have internal sensors for feelings, and I'm thinking about feelings of hunger, which increases with physical and mental exertion and is reduced with eating. There's the feeling of pain, which would go up with the number of collisions, but would be reduced automatically with the passage of time, simulating healing. And then I'm thinking also of the feeling of ennui, which goes up is if a GM is not learning anything, if its logic programs are unchanged for a long period of time. But ennui goes away when the GM is learning. Feelings have a balance, positive, negative. I'm hungry, very hungry, negative balance. I'm not hungry at all, positive balance. And a negative balance signals risks to homeostasis. And when beliefs are derived from feelings with a negative valence or a positive valence, then these beliefs take on this valence. And this is going to be used to prioritize actions, because actions that promote beliefs with a strong valence will be prioritized over actions that do not. So, in other words, a GM with very strong feelings will have its actions prioritized over GMs that currently want to take action, but from less feelings, less powerful feelings. And if these actions conflict, then the actions of the GM with stronger feelings will predominate, will take over. Well, given all this, what do I think makes a robot an active inference robot? Well, there's many things, but I'd like to think that in its simplest expression, for me at least, an active robot is one that learns what to do in order to feel good more often than not. So I'm hoping that this work will raise some big questions and give me some insights into them. For example, what is the a priori knowledge that an agent must possess to learn autonomously? What makes unsupervised learning converge on competency, diverge? And maybe a little bit more far out, what can growing a society of GMs learn from developmental biology? I suspect that there are principles at work here that they both share. So that's it. Thank you very much. Thank you to the Active Inference Institute for their help and encouragement. The version 3 of my work is available on GitHub. It's open source. I can be reached on Discord and by email. And the companion paper to this talk is available on Zenodo.
All right. Great talk, JF. We'll take a quick break and we'll be right back with the roundtable. All right, we are back. This is the beginning of the second roundtable. That's our last session in the second interval of the second Applied Active Inference Symposium. And some more may be joining, but I'm joined here by Adam Safron, Bruno Lara, and Jakub Smekal. And maybe just to begin, it would be awesome if anybody who wanted to... Thank you. And welcome to JF. Karl will be joining shortly. So perhaps to begin, if anybody would like to provide a reflection on a talk that was not their own. What was something that you felt like was brought to the table? What was a key problem area that was addressed, and how did you see active inference being implemented and adding meaning in that situation?
I can maybe quickly just comment on JF's presentation since it was the most recent. I think definitely this symbolic approach to active inference is one that has perhaps not been that pushed forward and like obviously there are different approaches all around the field, but I feel like that this particular perspective on pursuing this kind of emergent generative models, which only have the very basic kind of setup, but then the complexity emerges through the usage of Elixir and Prolog, I think was really interesting. And yeah, I mean, we've talked about JS project in the organizational meeting units quite a lot, but every time I think about it, it's really cool to see this implementation.
Thanks, Jakub. Adam?
Well, I mean, in terms of the recent one, just the apperception engine, like the Kantian inspiration that I found that to be really exciting, especially because I've been taking some inspiration from Kant, some of the work, and like wondering whether basically like these categories, like are they not just like preconditions for judgment, but like any kind of sense making whatsoever, like any sort of world with composition that could be navigated and parsed. And so to see that that kind of work was being done with that level of sophistication was just amazing.
It is a thread that came up multiple times with juxtaposing discrete time, continuous time, and all of these. And then it's almost like another dialectic with the numerical and the distributional approach to variational inference, sampling, message passing, a whole taxonomy of approaches that we've seen for active inference models, and also models of perception, cognition, and control outside of active inference. And so maybe, JF, if you wanted just to provide a thought on where you see the symbolic perspective coming from and intertwining with active inference directions and robotics like we were talking about today.
Right. Well, I think it comes in from different perspective. One is explainability of choices and behaviors. If the robot is driven by symbolic reasoning, then it becomes relatively straightforward for it to provide an explanation of its behavior in terms of the chain of reasoning that led to it. So that's of interest in and of itself. The other aspect is when it comes to the apperception engine, is it has an ability to develop a causal theory, a symbolic causal theory from relatively small data set. So unlike machine learning solutions, which require an intensive learning process, which leads to an obscure causal theory, if you want. With the apperception engine, you have a relatively small amount of data that as input, and a causal theory that's symbolically expressed as output, which can serve as a basis for explanation and justification and rationale. That being said, if as part of the process of apperception, a GM abduces latent objects and abduces predicates, the meaning of these predicates are only to be inferred in context, because they're going to be called like P1 and P2 and object O1, object O2. You may, by examination, just maybe infer, I think we're looking at a predicate that has to do with navigation and avoidance, but that will not be clear. So I think in that regard, there are gains, but they're not absolutely clear in terms of explainability. But when it comes to active inference, I think that what matters to me is that the robots behave according to the principle of active inference and not necessarily by implementing the mathematics of it. So I don't think it's in contradiction. As far as I'm concerned, these are affordances that our mind, just symbolic programming. And that's why I'm doing it that way.
Thank you. It's almost like in the textbook of active inference where we have the high and the low road, and here's like the symbolic airdrop actually arriving at a similar place, although being quite disjoint in its origins from the particular partition, flows on continuous numerical variables, a lot of the ways that we've seen things develop in the past several years. So welcome, Karl. If you would like to say hello or provide any remarks on anything that you've seen at the symposium or any overview thoughts on active inference and robotics.
Well, I've greatly enjoyed all the presentations. There's so many different perspectives. So I would imagine my comments will follow on from what people want to talk about. So I'm going to just pick up on that last theme. So, Jean-Francois's symbolic dropping on from high, I thought it was a really intriguing perspective. And it's a perspective that I've been actually forced into in certain applications of the good old-fashioned mathematics of active inference. So I thought it'd be useful to share that in the sense that when you write down discrete state space models and use the maths of minimizing variational expected free energy to invert those models, very often you're confronted with specifying those models with Boolean logic, if this, then that. Literally in the code which you write to specify a particular tensor that maps from some causes to some consequences, you are literally using if and then statements and or statements in order to generate the tensors or the matrices that sort of encode probabilistic mappings, which now become deterministic mappings simply because you're populating these tensors with zeros and ones. So I do see an enormous opportunity here to actually bring together the mathematics and the simple probability theory, just using categorical distributions or Dirichlet distributions of a particular sort, where you're only dealing with sort of zeros and one probabilities, and the kind of logic and apperception that you were talking about. I thought that was absolutely fascinating. One thing that intrigues me is if you can do that, then there is a way of doing your searches of all the potential programs or logical statements that are internally consistent with the evidence at hand. For example, I could build a generative model where I can be in two places at the same time, or two things can be in the same place at any one time. That's, from the point of view of the generative model, I can write that down without an exclusion principle. But when I now come to ask the question, is that model relative to another model that can be written down in terms of Boolean logic that precludes two things being in the same place at any one time, does that simpler model now provide a better explanation for the evidence at hand? So technically what that means is that I can apply the rules of Bayesian model selection to this model versus that model, where the model just is a statement of propositions, logical propositions, and there are ways of sort of automating that very efficiently, called Bayesian model reduction. And I'm just wondering whether you could take a lot of pressure off the search for the internally consistent logical structures that you're dealing with, if you can cast it in terms of in terms of Bayesian model reduction, which quite simply is just measuring the evidence, the probability of this sequence of outcomes. That can itself be categorical, I'm in this state or that state. The probability of that particular sequence of discrete outcomes given this structure, this generative model that is articulated as a logic. And if you can do that, I think that'd be very, very powerful, because that speaks to a common theme, which I think most of us or you were talking about, which is this issue of structure learning. And what you're talking about is sort of a principled way to get the right parsimonious structures that have this this coherence. I can't remember you were even taking it right back to sort of 19th century philosophy or 18th century philosophy in terms of the constraints. It would be really great to see whether that kind of sort of logical structure that philosophers like actually could be discovered or disclosed just using good old-fashioned Bayesian model selection. There seems to be a close homology there with some of the work of people like Josh Tenenbaum, where he certainly articulates structural learning from the point of view of radical constructivism, using sort of program searches and sort of casting generative models as programs, and then trying to score the quality of these programs using a form of Bayesian model selection. And he claims to be able to do sort of millions very, very effectively within a few seconds. Have you looked at Josh Tenenbaum's work at all?
Not yet, but I certainly will. And I just want to make clear that the apperception engine was developed by Richard Evans in the paper "Making Sense of Sensory Input." And yes, one of the core issues is inductive bias. How do you restrict the search space so that you can have a chance of finding within a reasonable amount of time a logic program that is a competent predictor? And that's where Kant's synthetic unity of apperception plays in, as it provides constraints on the class of logic programs which are acceptable, which are considered valid. And if I make a contribution, because this is work in progress, I would like to add additional constraints from the fact that we're not trying to generate one generative model in and of itself, but as in the context of a society of generative models. So a generative model will borrow its perception domain from the belief domain of other generative models, thus creating additional constraints. And as it searches, it will try not to modify its scope in such a way that it orphans other generative models. So as the society of generative models grows, so does the set of constraints that apply on reducing the search for a predictor in any of the generative models themselves. So I'm hoping that as the society of generative models grows, so does the set of constraints that apply on the searches for any one of them. But I think the name of the game is very much in this, the richness and the strength of the inductive biases that are applied on search.
Just to highlight a few pieces of what were addressed, and then to Bruno or Adam or anyone who'd like to add. It impressed on me, robotics is radical constructivism, not just in the sense of the constructing models, but also in the way that Adam described in terms of the relationship to the embodied artifact. So that is one interesting piece. And another, in this quest to find the rainbow that connects first principles and analytic formulations through mesoscale, for example, computational code, all the way to the last mile in the cases that we heard from Wen-Hua Chen in the previous session. Karl, when you described the way that Boolean logic enters at the level of execution was very interesting, and suggests that there is kind of like a brackish area similar to that between discrete and continuous time models in like hierarchical modeling. But here, where the numerical and the statistical approaches to active inference are becoming connected to actual logical implementations and design choices that have to do with which functions are executed first, or the conditions that certain things occur in. And so there actually is a meeting ground or an interface in a way implicitly already. And so it is very interesting to see how JF's work on the generative model generation process is now approaching that intersection from the other side and suggesting it's like if you see a car coming from the other direction, there's a road. And now this high and low road network starts to grow more pathways. So Bruno or Adam would be happy to hear any thoughts you have.
Yeah, thanks. Yeah, I mean, I think that's much our case. As I was telling you, like we come from this other side of the story, and at the end we have to make some choices on implementations. And so far we've been very focused on these self-organizing maps. Most of our work is on that. And that's actually one of the questions I had for all of you. Like, what's your take on all these approaches that we're trying to, like, we're coming from a different field, from a different point of view. And in a way, we are almost intentionally avoiding probabilistic approaches to active inference, no? So I don't know what's your opinion on that. That was the first one, and the second one is more like I don't know, like a doubt, a question for Karl. Like, what do you see in the near future on all these things that we're working on prediction error dynamics and this monitoring of the error over time? I think that's.
I'd love to speak to that if I can, yeah. In fact, interestingly, it does actually also speak to your question, Daniel. I just wanted to point out also that this notion of moving between continuous state-space models and discretized state-space models is something that people in quantum computing and physics are going to keep their close eye on, because if you get it all digital, then the opportunity for quantum computing suddenly rears its head. So I think there's also a very pragmatic reason to sort of look at that transition. And also, just to bring in Adam's point, not only was he suggesting that we quantize, discretize, spatialize in terms of little tiles and places, receptive fields for being here as opposed to being over there, but he was also suggesting we do that in time. So I think the quantization of space-time in a generative model is a really important thing. And of course, you could argue that that's a step closer to good old-fashioned symbolic AI that has a meaning in the sort of folk psychology sense. So to come to Bruno's question, so the big divide here is between, from my point of view at least, generative models that are of continuous states and time versus generative models that are of discrete states and time. And clearly you need both, in the sense that the world that a roboticist, and indeed me and my children live in, is a continuous world. I have to move around it. I have to control continuous temperatures and all sorts of things. And yet it seems as if the intelligence is at a symbolic level. So I think what we're talking about is a hybrid generative model. And then the question is, how do you get the sort of discrete parts to talk to the continuous parts? But if we just focus on the continuous parts, and just to answer Bruno's question directly, well, first of all, what I'm saying is you can't ignore the continuous bits. So everything you were talking about in terms of self-organizing maps has to be there at some level. It's just a question of whether you can put a more symbolic logical structure on top of it to coarse grain it sufficiently to resolve all the complexity. I loved your work. I could see all the important issues in terms of representing uncertainty as the, if you like, the stand-in for the valence of how I am doing. So I was amused to hear that you're actively avoiding probability theory. Yet for me, everything you said was all about probability. It's all about uncertainty. And that was true at so many levels. So just to answer Daniel's question to you, the relationship between variational free energy and the prediction error is really trivial and very simple. It's just under continuous state space models with Gaussian random fluctuations, the free energy gradients just are the prediction errors, the signed prediction errors. So it's really, simple quadratic forms for the log probabilities. Self-organizing maps that organize themselves in terms of responding to prediction errors just are systems that are performing a gradient flow on a variational free energy under the assumption you're dealing with continuous states that have Gaussian by central limit theorem, Gaussian random fluctuations. So that's all exactly what would please me if I was a probabilistic committed to the probabilistic parts of it. I think you're bringing to the table, though, is this sort of the dynamics of the uncertainty or the amplitude of the prediction error, the unsigned prediction error, the sort of the behavior of prediction errors over with the separation of timescales. And I think that's a really important move. I see slight homologues of that, not formally identical, but certainly homologues of that. From the point of view of an engineer, this would be like getting the Kalman gain right. If you interpret a Kalman gain on a Kalman filter as assigning the right precision or confidence to the prediction errors as they come in relative to the state estimators and your prior beliefs that you've accumulated, getting that right, having an adaptive Kalman filter where you're actually optimizing the Kalman gain. That would be, if you like, the state-of-the-art hierarchical Kalman-Bucy filtering. So that if I was a psychiatrist, I would say this is exactly what goes wrong in people with schizophrenia and autism. It's that they've got their estimators of the overall uncertainty or prediction error wrong, and that they now need to, and that this is an explanation for false belief updating or false state estimation from the Kalman filtering point of view. The other point that struck me in the early part of your talk was something which, as a neurobiologist or motor control theorist, something that they would find very entertaining, which was the link between the ability to ignore stuff and sensory attenuation. I don't know if you've come across that in robotics, but certainly in terms of motor control of the kind I think you're using, which I would ascribe to the equilibrium point hypothesis like approach. So you're putting your set point into the actuator and you're letting the reflexes do the rest, but you've got to control carefully how those prediction errors are used to drive the actuator and make sure they don't come back up and change your state estimation. And so from the point of view of sensory attenuation, that just is attenuating the precision or the inverse variance or estimation of the overall amplitude. So, and finally, looking at the long-term trends in the estimated precision, I think is a really important way to see whether you've got the right generative model for this context. And I noticed you're citing the work of Matthias Joffeli, and that was, I think, his really great insight many years ago. Interesting from economics, he was working with economists at that time. So I think that's very, very important as well. It's all about estimating uncertainty.
Yeah, thanks a lot. I mean, as you can see, there is obviously we come from this side of Wolpert, and you can see all that all that literature behind our work, and but yeah, we're getting there, and that's where we are going. That's what we're intending, and you'll see some work that we're going to come out very soon that tries to bring deeper this to make more useful, make better use of this monitoring. And the other thing I was thinking is something you mentioned is this weighting of the attenuation, and that's always been in our mind, again, because of why can you tickle yourself and all these famous works. We have lots of doubts. We have lots of discussion with people about this attenuation and the precision weighting, and that's what we are now trying to implement. again using self-organizing maps. But yeah, we'll try to get results quite soon. And thanks a lot.
Yeah, just to say, if you, I think that's really important, because as soon as you can get dynamic attenuation or gating in play, very much in the spirit of what was implicit in Matt's sort of homeostatic architecture, you can talk. I think genuinely you can talk about your robots attending to this or ignoring that in the right kind of way, and you're starting, I think, to get quite close to now sentience, because you've got attention in the mix. You've got a kind of metacognition in your self-organizing maps, which I think licenses something which is much closer now to sort of a sentient intelligence, as opposed to just a reflexive kind of control.
Yeah, that's the idea. Let's hope for the best.
So, a few points, and then Adam or Jakub or anyone. Active inference is inference about action, and it also uses action as one of the ways to reduce uncertainty. And so it's a very tantalizing parallel with quantum active inference as being about quantum systems and potentially using quantum in some way to run these models. Another point was in the recent folk psychology paper with Ryan Smith et al., there was a distinction of how increasingly cognitive and symbolic functions were being played by decision-making active inference in the discrete setting, while more motor behaviors could be played out by motor active inference in the continuous time setting. And through this conversation, I'm seeing how, whether that is explicit or implicit, that decision AI to motor AI handoff is mediated by a symbolic layer, either implicitly through the code construction or potentially even explicitly with the kinds of approaches that we're exploring. And then one last area of some parallels that I'll like to hear from Adam or anyone else. Self-organizing maps brought up by Bruno have a lot of similarities with some of the graph operations that Tim Verbelen and Ozan Katal and Adam's work was describing. And then the harmonic modes that Adam has described in work as well reminded me of the ultra stability that Matt Brown described in some of these more classical models of like synergetics and multi-scale harmonic organization. And so Adam or anyone else would be happy to hear any of those thoughts.
Okay, just quickly to answer Adam. I don't know exactly how. I mean, what do you mean with
by the way, they can't see my question. The audience, so maybe we should read.
Sorry. Adam is asking, to what extent can self-organizing maps be used as model of experience-dependent plasticity, as implementing a kind of implicit neural architecture search? I mean, I don't know exactly what you mean with neural architecture search, but there is this literature on growing self-organizing maps. So like the usual original architecture is fixed, but there is some implementations where you actually can add nodes, and they become more well, they have more plasticity. And there is also the ones that don't stop learning, so it's continuously moving. So that helps you to not have a fixed structure and a fixed mapping of the sensory input, but it just moves as there is new data coming, new input coming in. So that's two dynamical sums and growing sums. I think if you are interested on that.
Extremely. I guess the intuition or question was that it's like, I'm sure there are plenty of inductive biases that we become equipped with to help us converge on efficient regimes of inference and learning. But I'm also wondering the extent to which, I don't want to go too far with this kind of analogy, but something kind of like a field programmable gate array, but like that self-organizing map like dynamics could allow for the creation of different regimes of active inference? Like to what extent, as you're like, let's say, building up a hierarchy, at different levels of it, based on where you are in this overall hierarchy or hierarchy, you might take on very different computational properties via experience-dependent plasticity. So it's like you learn the inductive biases you need as you go. But to come back around with self-organizing maps, the locality and the topography of them, one thing I'm really curious about is the extent to which they could actually be used for modeling like entorhinal and hippocampal representations. To what degree the different operations that are used for constructing these maps would also converge with the kinds of structural inference and structure learning that have been described for the hippocampal system. So I don't know the answers to that, but it seems like a potentially fruitful intersection that Daniel suggested. So
yeah, definitely. Yeah, I mean, I think in principle they are inspired from hippocampal activity, no, the maps, and yeah, there's lots of proposals out there of different ways of moving them, but yeah, I think they would be very useful for what you want.
So while I'm talking about that, like a general question for me that I've been wondering about is, so I guess I'm suggesting that like you're getting these representations, structure representations potentially being afforded by these place fields of the hippocampal system. But one thing I'm wondering is, so, and that these would provide like equilibrium points. Like Karl often will talk about the importance of structuring action and perception by these discrete acts that seem to be unfolding at roughly theta frequencies. And this seems to be like the time scale of coherent action selection for an organism of about our size that can do about the things we can do with a brain about this big, all kind of brought in the same temporal register. And so this idea that like we might be stepping along these representations in some ways, like moving from like between these bump attractors, as somehow structuring cognition by some sort of representation. I'm excited by that, but I still don't have like a sense like for how far you go with that or ought to go. Like for instance, so let's say we're talking about something like, this is actually something Karl said, scolded me about in the past, which is like before you like think of the architectural principle, think of the inactive situatedness of the system. And so something like I wonder is like, so, you know, I'm focusing on like maybe you're getting this sort of inductive bias of like the hippocampal entorhinal system as this high level controller, but to what extent are we implicitly doing things like symbolic reasoning, but via like modes of enactment? Like to what degree, like could you do something like let's say we're talking about like Pearlian causation, and you want to do something like a do operator. You could have some sort of like graph, some sort of like flow of inference, like maybe even like within like the like chain bump attractors of like the hippocampal system. And actually another thing that Karl actually brought up recently was bump attractors in the colliculus. So maybe even like in terms of like patterns of like ocular motor motion is potentially like providing a, like another means of accessing such representations and being governed by them. But to what extent is I don't know, is it too neurocentric? Is it actually like being realized more implicitly by the overall contextualized functioning? And like it's, you know, it's open questions for me. So.
Sure, to Karl, and then Jakub, or anyone else who wants to talk.
Well, to me, well, can I tell Adam off again, or not? I don't think he needs telling off. Yeah, it's interesting, isn't it? I wonder whether that is the interface that Daniel was referring to. How do you get from a necessary continuous sort of Bayesian filter coupling with the world? I mean, even with Carla and Andy, you know, these things are moving continuous state spaces. So at some point, even if it's actually physicalized. There is a continuous generative model or self-organization in play. And I'm reading Adam's question as, is this too neurocentric to worry about bumper tractors and the role of lateral inhibition, for example, in carving up receptive fields that could be actually written down as just sort of basically a quantized representation. For example, receptive fields in V5 or motion sensitive areas can either be expressed as a sort of continuous preference for motion as a continuous function of visual velocity. Or you can say, no, this population is just encoding the probability that this particular edge is moving at 8 degrees per second. So, if Adam, you were asking, are we being too neurocentric in over-interpreting the neuronal dynamics that just basically do the carving up into a series of either tilings and receptive fields or place fields, or in the context of sort of stable fixed points, thinking about heteroclinic channels as one way of articulating a discrete set of ordinarily organized fixed points that have that's the way that we should understand it. I don't know, but I think it could certainly, if you can read them in both ways, I think that then gives you license, if you wanted to simulate and reproduce in silico these kinds of computations. It certainly allows you to replace heteroclinic channels, heteroclinic cycles, bumper tractors, receptive fields of this kind with a discrete representation. And to me, practically that would be an important way to proceed. Simply because that minimizes the complexity of the generative model, and in minimizing the complexity, you maximize the model evidence. So I don't know whether being neurocentric is a good thing or a bad thing. Interesting. Just think about what is a self-organizing map. So when I was at school, it was just basically a couple map lattice with lateral inhibition to do this sort of carving up and segregate those various populations or localities from other localities. So if that's the case, again, you've got this notion of lateral inhibition. We're going to take all light dynamics. What is that? Well, is that a statement of this exclusion principle? And I mean it beyond simply the sort of exclusion principles. I can't be in one place at any one time, but the fundamental exclusion that you get when dealing with discrete state spaces. I've got to be in this state and I'm not in any other state. And that means that being in this state means I have to inhibit being in any other state just to get a sum to one constraint. So just by going, if you like, discrete, you're naturally inducing a biophysical architecture that requires the kind of lateral inhibition that is one of the defining features of a self-organizing map. So that might be a virtue or of being a bit neurocentric in the sense of understanding evolution as working its way to a coarse-grained, minimally complex, discretized, symbolic representation of the world, and that we just now read receptive fields in a slightly we overinterpret them. They're just basically encodings. The world is likely to be in this state from my point of view. Can I just make one final point, which kept on recurring to me? There'll be people chasing you on this. I'm thinking about Bruno and self-organizing maps, and Adam in and actually Matt as well with his. I think there's a slow realization that these kinds of architectures are the way to go. That's coming out of machine learning when people are getting bored with backpropagation. So they're now all turning to local energy based rules, and they now realize that they get much better performance from a deep neural network if they just use a local energy based rule. And what would that look like? It would look exactly like the self-organizing maps that all three of you have been talking about. It's just me, my node, trying to predict everybody else around me, and doing so by minimizing my local variation free energy or minimizing the prediction errors, mathematically, those being equivalent. The twist here is that this can be applied to effectively an overly expressive, amorphous, a completely connected neural network, and it will still work. With the right kind of pruning, you will start to get to the sort of nice hierarchical structures that Bruno was showing, or with the right kind of temporal scheduling, you'll get to the nice, Tolman-Eckenbaum machines. But at the end of the day, these are just they're just sort of deep networks, or not even deep. They're just networks with a local energy. Those things I've now noticed, certainly at the University of Oxford, are now called predictive coding. So there's necessarily no prediction. There's no prediction in the temporal sense that Adam was trying to emphasize, or in the sense of a Kalman filter. It's just that they rely upon the local computation of prediction errors to generate the local energy function. So I see, the reactionaries in deep learning, the young Turks who want to do it better, they've all now identified predictive coding as the rhetoric in order to say this is how it's done, and it's just a statement of you don't need to do. I think Bruno had a nice phrase, or perhaps it was Jean-Francois. Diffuse your learning everywhere through backpropagation. If it's working properly, you should just be able to do it locally with your own little node vertex of your SOM or GM in Jean-Francois'.
If I could build on that, and then anyone else who'd like to add, a challenge that exists and is recognized in robotics, and many of the presentations brought up, was how to move from continuous and high dimensional data, like a high resolution video camera or multi-sensor integration in the world, eventually towards logical and conditional contextual action. And so when we see the neural network representations, we kind of see sometimes zooming in and zooming out, and different ways that people are training those models, including limitations in those models training, like the backpropagation that Karl just mentioned, as well as that Stephen Grossberg has gone into. And so trying to contextualize that issue in light of what we're discussing about discrete time and about symbolic logic, it seems that through the partially observable framework, not even saying the partially observable Markovian framework, but here including holographic principle and so on, there's a way to move from a continuous statistical distribution and make a map to a discrete statistical distribution. Like the A matrix in the POMDPs that we use can have a continuous variable and then map that onto a discrete statistical distribution. And then I wondered if there's something like a logical A, another tale of two densities, a tale of two different cities, or a third city. And so this matrix recognizes logic from discrete distributions. That's the recognition density. And then the generative density is the emission of logics that are compatible with discrete distributions. Because with the recognition direction, recognizing conditional logics and searching over relatively small sets of possible conditional logics from discrete distributions is possible. Like a verb is never used, two verbs in a row are not used, or something like that. From a discrete distribution, logic could be extracted or recognized. And then if there's a discrete distribution or more, logics can be sampled, and that speaks to that inductive bias, where you want the inductive bias to have limited false positives and false negatives with respect to the empirical world. Like you wouldn't want to waste time spitting out logics that cannot be. However, that might not be lethal, but it certainly wastes a lot of time. And then conversely, what could be lethal would be to have an inductive bias that fails to recognize empirical aspects of the world. And so that is like an expectation maximization, but transposing not between a continuous and a discrete statistical space, but rather between a statistical and a logical space. So Jakub, Jakub or Bruno, anyone who would like to add to that, please.
No, Jakub, you haven't said much, please. But yeah, I can say something afterwards.
Yeah, I just had some general questions that are kind of related to Daniel's remark on the move between the purely continuous and statistical representation of the generative models into the discrete. And since this week I've been reading the paper on from Chris Fields and Karl and others on the FEP and neuromorphic development, I'm wondering whether the question of structure learning can be solved by some fundamental computations that are available at the very low dimensional level of just quantum systems, where given the right environment, that system would naturally evolve into some kind of discrete morphology that it didn't start with, kind of similar to like the primordial soup, then evolving into discrete or more discrete life forms, and whether that might impose the necessary structural learning principles or message passing, where each new layer that evolves in the hierarchy is receiving observations from the other ones, given by the new Markov blanket that's drawn around it. But then in terms of actual implementation, I'm wondering whether that requires quantum computers or whether that can be done with some kind of different architecture that is able of this automatic evolution in its morphology.
Also, Bruno, and then anyone else who'd like to add.
Yeah, very nice your question, and then just kind of to round up what you were all concerned about. We were just thinking and remembering this and going back to sums. And there is this proposal, some sums, but I don't remember the authors now. But it's this other type of architecture that takes into consideration the learning progress. So previous activations and some sort of history of the previous winning nodes and so on. That might be the next step, so that you can actually monitor what's happening over time. And if you have one of these that it's coding for error, then that would include the monitoring of the prediction error. Yeah, and it would kind of close this gap between continuous and discrete representations, because then you could have it all over time. So if you want, Adam, I can send you some literature on that.
Thank you, Bruno. One point on the morphological computational angle, Jakub, and then again, anyone can raise their hand. I thought about a bunch of tree seeds. We're back in frequentism again, so everyone can take a breath. But there's 100 seeds that are planted, and depending on the priors inherited from evolution and the updates which are happening from the generative process, from the niche, there's going to be like a distribution of that tree through time. So like a palm tree is going to have a very like narrow cone, some sort of distributional cone across those 100 that are sampling from it. And then a shrub might have like a different shape. Then you brought up how potentially quantum or discrete like morphological decisions could realize that continuous probability distribution at the population or even like the multiple worlds level. And there's something there also with the local computation of large models that Karl mentioned, that it's like something happens where there is not even just a symbolic or a discrete decision that's made. There's an embedded decision that's being made that now is part of the history. And so the branching pattern of any given palm tree is going to be unique, or any given shrub, yet they also may fill out at the population level a distribution set that has these aspects that can be modeled as like a Gaussian blur over tree morphologies. Yet, of course, no one is saying that the tree is a blur. And so there's so many interesting contrasts with like the realized trajectory of the Lego robot. And that's the n=1. The population of trajectories, the imagined set of trajectories. So having a unified ontology to be able to talk and have formal, concise connections amongst these different kinds of remembered, now casted, anticipated, or imagined futures helps find the patterns across systems that, like Adam said, are essentially the basis of sense making and insight.
I got to ramble. So I guess in terms of this, like motion from a continuous to a discrete regime, or even like I'm drawing analogies from like a quantum to like a more classical regime. There's in general, like I've been kind of like with respect to computational models of consciousness, wondering how a seemingly classical world of experience can emerge from a probabilistic model. Like, why are things so precise? And Karl's written some really interesting papers with Andy Clark on this, on the Bayesian blur problem. And one of the suggestions was that like the discretization for the sake of action. Like, in order to act, you have to act in a particular way, and it's like just the requirements of doing a particular thing at a particular time induces this. And so one of the things, and so this is, I don't think it's competing, but it in some ways competes for like a suggestion I had, although I think it's compatible, because like I was wondering whether basically like something about the timescales at which you could get like these coherent eigenmodes, or like the population activity could achieve these like attracting states, would create like the timescales of the formation of these large scale attractors could create like an in and an out of like who gets to inform or not, and this could help to like sharpen things up and like creating these population level attractors. But there's another way of describing it in terms of like what lets you act. So in terms of like these different I guess one more comment along those lines is I think it's interesting that like, so I've talked to some rodent researchers, and when you remove the hippocampus, you'll still actually get like roughly theta scale like large mesoscale organization of brain dynamics for the rest of the rodent's nervous system. So it seems like there's almost a it might be, I don't know if you say it's like degenerate, but it's like natural selection, like any mode, any way it could canalize things to help with the coordination, to help with the alignment, the spatiotemporal alignment of that could allow for different forms of synchronization, was utilized. So like there's like, you could get, for instance, a good amount of discretization just from like potentially just from like learning and interacting with the world that requires you to do this just physically to interface with it. You get some of it from like the overall connectomic properties, just like that's the times, like that's what's required for the overall brain to form attractors. They'll form it at a certain time scale and different nervous systems of different size and complexity with different information bottlenecks might tend to form these attracting states roughly on that same scale. And maybe things are tuned for that, or maybe they get tuned by experience, either as an innate inductive bias or as a empirical meta prior learning or learned. You can also get it with things like the local logic of like how you transition between these different equilibrium points for like highly central structures. And so something that's very unclear to me is like the extent I imagine the answer is like all of the above in like most combinations, but it's like, to what degree were these inductive biases, are they taking the form of evolutionary priors, and to what degree are they developmental priors? This is still very unclear to me. But one thing that, and there seems to be a tension in machine learning in terms of these, like, you want these rich inductive priors to do efficient inference and learning, because otherwise it's hopeless, but you pay a price in terms of generalization sometimes. And so I have no idea how nature balances, to what extent and in what cases. Or I have some idea, but not nearly enough to feel comfortable. So anyways, that's my ramble.
I think we can actually hinge on this and bring it to an area that some of the registrants brought up, and also something probably many of us have been thinking about, which is multi-agent modeling. And I wanted to connect that to what Adam was just saying about what is granted via embeddedness. What arises or becomes more possible simply as a function of realized corporal embodiment as opposed to in silico simulation. And in our multi-agent discussions, we've been differentiating spatial multi-agent scenarios from essentially non-spatial, like digital or cognitive. So in the spatial multi-agent case, the real world, the niche, the generative process does the work of inducing or preventing collisions. Like, it just cannot be the case that two entities are in the same location. Whereas in the cognitive case, whether it's birdsong or a negotiation or verbal communication, or we're visiting websites, we can both be at the same website. And so then there's sort of a mass parallel stigmergy occurring, or a mass parallel real-time architecture where there is some kind of coordination, but the coordination isn't exclusionary, again, because two entities their thought trains could essentially cross in and out. And those trains are like ghost trains that don't exclude each other, whereas that couldn't happen in the real world. So I wanted to ask anyone who had thoughts, how does multi-agent modeling come into play for robotics? What current issues are facing multi-agent robotics? And how can what we're discussing here with active inference play a role specifically in understanding complex multi-agent scenarios?
I have a question in that regard for Matt. Matt, your solution has been applied to a single agent. Do you see the possibility of a homeostat that is composed of multiple agents that will direct their collaboration towards achieving a common goal? Does it scale to multi-agent situations?
Thanks. I hope Matt can provide a thought as is working. Karl, and then anyone else.
Where is Matt?
Listening.
Oh, is he? Can he speak?
Only at a future point in an expected trajectory.
I will answer for him then. I would imagine what he would say is, if you just take the generalized synchrony perspective on with the emergent properties of a homeostat coupled to its environment, and you couple two homeostats together, they will find a mutual homeostasis that just will be a joint synchronization manifold. So what you'd expect to see is a coming together exactly in the spirit of dynamic or generalized synchronization. So there will be, as I think Daniel mentioned earlier on, the homeostats will be singing from the same hymn sheet under the constraints of what they can communicate. So I think from Matt's point of view, he's more interested though in establishing a generalized synchrony between a use case, an industrial use case, and his homeostat, as opposed to just letting two homeostats, shape and design their own little eco niche and indulge in sort of cultural niche construction. While I'm talking, though, I think there's a nice something very interesting about Daniel's question in relation to your work. I sort of overheard the little robots telling each other what they were thinking, and I thought that was really important. And simply because, speaking to this general question about, what does active inference, or what are the special considerations that you might want to bring to the table when thinking about a multi-agent setting? I think there are two ways, and we could talk for ages about this. First of all, it's having the law of requisite variety across agents, and then the story would unfold in terms of natural selection as Bayesian model selection, and that would, I think, answer in large parts of Adam's questions about where the inductive biases come from. If you cast the biases as selection biases, we're just talking about Bayesian model selection amongst what? The requisite varieties afforded by Ashby's law. But to make that Bayesian model selection work, you have to have natural selection. So there's a great story about the importance of multiple agents from that point of view, from the point of view of structural learning for free as an emergent property of natural Bayesian model selection or natural structural learning. But the other thing is, just from the point of view of active inference, if you've got multiple agents, what's to stop you thinking about these multiple agents as one big agent where you've cut some message passing between them, and like one big agent with lots and lots of eyes and sensors and the like? So I'm asking now, when I looked at Carla and Andy, what's to stop me thinking about Carla and Andy as one agent that has a really flexible and deployable set of sensors? So they've got eyes that can point in different directions. So if we translate this into sort of controlling drones, for example, and we have a swarm of drones, we could think about that as one agent, one robot with lots of deployable eyes, which gives you, an enormous flexibility over and possibly complexity of the way that we control our two eyes, which are both in front of our heads. So how would you then write down a good generative model for a swarm of eyes, where there's one CPU, there's one sort of I can't remember, the Lego brick controlling all the drones? Well, you just write a generative model with multiple sensory modalities where you needed to deploy action in the right kind of way to get the right epistemic foraging or whatever. But that would entail now message passing, belief updating, lateral interactions, and an SOM between the brains of agents. So say, you can't do that. You've actually got to have physically separable robots to have a truly multi-agent setup. So how can you now work around the fact you don't have direct message passing and belief updating between the brains, the separated brains? Well, you just have communication. So provided you broadcast what you believe, and provided those beliefs are perspective independent, so they're conserved from, so that they, what I say in terms of my frame of reference is meaningful from your point of frame of reference, which incidentally for Daniel and Jakub becomes relevant from the point of view of quantum frames of reference here. But if we can assume we've all got an allocentric frame of reference, then all that is required to put together the many brains into one brain is to have beliefs broadcast. Just those beliefs that are conserved or shared in the ensemble's generative model. So I don't know was Carla able to hear Andy and vice versa? So did they actually share a narrative and a belief updating?
No, they did not. The speaking was the talking was mostly for my benefit, so I could see what was going in their mind at the time. So when Karl was saying, "Oh, Andy is freaking out," I knew that the generative model had identified the behavior and inferred the mindset of the other robot. But I am playing with the idea that they can communicate by just distributed message passing from one robot to the other. And what they would communicate is essentially, I would consider one agent as a source of sensation for another agent, and in the same way that internally generative models, the beliefs of a generative model becomes the sensation of another higher level generative model, that can scale across multiple agents, and that would happen by communicating these predictions across agents, and these prediction errors across agent as they propagate between generative models within a single agent, and just scale the architecture. So instead of having a society of mind within an agent, we should also have a society of minds across agent, and the same mechanisms would be at play. But you're absolutely right. We would need to have this communication, but it would be the same kind of communication within across society of minds as they would be within a society of mind. I'm hoping that it would be self-similar, and the same architecture would apply at any scale.
Which actually speaks to Jakub's question about Markov blankets and Markov blankets, and sort of that sparsity you get from that scale-free separation and refined, minimally complex message passing. I think there's something quite fundamental there about the nature of communities and the scale of the world in which we live, and all the organs that comprise me living in that world. That scale-free aspect that is defined by the sparsity and the absence of coupling and getting the messages that are communicated right. I think something quite fundamental about that.
I got a question.
Yes, Adam, please.
So for the internal or organism internal case, I'm wondering, so to what degree do you get common agency for societies of minds due to common embodiment? But when we're going for a kind of common or joint agency, and maybe even different forms of joint identification or de-individuation or re-individuation of individuals into a collective, to what degree do we need something like as constraining as a joint embodiment? Like, for instance, like I'm thinking of like soldiers marching in step, or like the ways in which like we kind of like seem to like potentially even like expand and hack our body maps by like sharing like different synchronous modes. That literature is somewhat contested. I like the literature, but but to what degree is it? You don't need to have that kind of synchrony, though. It's just like a strong enough shared task is enough to like radically make someone make the central thing their role of where they're singing in the hymn sheet. That becomes the primary attractor governing them, and you don't need to like necessarily have this kind of physicality. I don't know if that makes sense, but like I'm thinking of the different means in which you get. Do you need something like synchronous in time, or is it just a very strong selective pressure for coordination to establish a synchronization manifold to pull off the re-individuation? I don't know if that's getting at any of what you had in mind, but
yeah. Oh, it's a great question, Adam. So thank you. I also think this ties to, again, JF's framing of society of mind, and then we can contrast that with a society of bodies. So the society of mind is that virtualized case, whether it's the counterfactual virtualizations that cognitive entities can be modeled as doing, or whether it might even be a society of minds in a digital setting. And then there's the societies of bodies, which maps earlier to our multi-agent discussion on like a physical crowd. So like, what are the similarities and differences with a digital swarm and a physical one? It comes down a lot to their ability to collide. And again, the digital swarm can weave in and out because they can coexist in the same location in a semantic space in that generalized foraging way. Whereas the embodied swarm is going to have collision prevention by virtue of the physicality. And I think by using active inference to study these systems and integrate them, we do approach exactly what you brought up, Adam, which is like, almost what do we get through shared task as opposed to what do we get from a common task, something that we merely have in common versus something that we're actively coordinating on together, and potentially even coordinating together in the same exact space or on the same instance of, which provides the most constraints. Like if people are rowing the same boat versus rowing parallel boats versus on different lakes. So as we sort of separate spatially and especially virtualize, there becomes more and more possibilities. And this, for those who are coming perhaps from a robotics angle and wanting to understand what active inference brings to the picture here, hopefully we've pointed a few things like the scale-free or scale-friendly nature of models to be composed based upon their sparsity and defined interfaces, and also the multimodal aspect. For example, Karl asked JF if the audio could be heard rather than only emitted. And that's not going to require some bolted on communication module. It is going to be able, in the symbolic or in the numerical case, to be mapped onto an architecture that also Bruno showed, these architectures that can do sensor integration as a function of the interface definitions locally, rather than potentially have ad hoc structural design decisions that could result in a lot of research and engineering debt. So happy to hear any thoughts on that. Yes, go ahead.
Yeah, I mean, yeah, you're right. And no, I just wanted to add that we are working on that community. Well, first, I come from the very, I don't know, like a very, now you could call it old-fashioned school, where we as you can see in our implementations, they are kind of very low level, what we could say low level, and coming from the sensory interaction with the world. And that is maybe why we are not, or we haven't been so far very concerned with very high level representations, no? So we are just dealing with very basic interaction with the world. And at the same time, it's my belief, I mean, it's very interesting, this interaction between agents and so on, but I think, I've always thought that first we need an agent that knows itself in the world and has its own model. So like a first frontier or a first blanket, as you like to call them. And only then can start to understand other agents and to interact with other agents. Yeah, so that was what I wanted to tell you.
Know thyself. Karl.
Well, I'm just wondering, there is an argument from developmental neurorobotics that to have a true sense of self, you've got to have a true sense of other, and you can only ever have a true sense of other if there's something else out there that's physically very much like you. So just speaking now to Adam's point, does it have to be, or perhaps Daniel's question, the shared body as opposed to the shared narrative? There is an argument. I'm not making the argument. I'm just saying that there could be an argument that in order to disambiguate the causes of some sensory consequences of an action from where the action could have been made by you or an identical robot, or me or mum, or me or my brother, that is the only case in which you are now going to need to contextualize and assign and attribute the agency of this outcome to self versus other. In a world in which I was the only object or phenotype like me, I wouldn't need a sense of self and I wouldn't need a sense of other. It's just when you have multiple agents that are quite similar and confusable then you actually need a sense of self to make sure it's you and not me, which of course, speaks to not only theory of mind, but the essence of communication as well. So I'm just making that point that that putting two robots together, maybe, as you point out, once you've sorted out a robot just learning how to move, then learning that the consequences of it moving could actually be reproduced by somebody else, and then it might develop a sense of selfhood, or a minimal sense of selfhood, and then I think you're in the game of true theory of mind. That's
Yeah, it's a very interesting area with thinking through other minds, as have been brought up in some of the presentations, and then society of mind. It is that nesting of blankets of different kinds of generative models, but again, using the same statistical or formal machinery, just like we could have a nested multi-level regression model where one model was in kilometers and then there was another model that was in degrees for temperature. And also the question about swarms and collectives and groups comes up in biology all the time, with different ways that people delimit or qualify individuality, ranging from the evolutionary unit of replication, the Kantian concept of an organism as the unit that is teleologically closed, the physiological individuality, which might even include cases like symbioses, the information theory of individuality, and different ways that we can look at information processing and transfer in terms of what individuals are. And it's so fascinating how that comes into play with robotics, where when we think about the robots that will be interacting with us as a slightly different set than the ones that might be working underwater on a pipeline, they're like Matt showed, they might be able to interact with a relatively simple generative process that doesn't exhibit mind-like qualities. It's interacting with a mere active inference entity. But when on the other side of the blanket, there's another adaptive active inference entity, and especially when it's us, then there's a space of norms and also laws, which are like that pseudocode execution order for thinking through other minds. In a way, how will robots navigate a space, and how will they be able to make abduction occur in a real-time way, both in the generation of novel hypotheses with inductive bias, followed by the selection of trajectories of action, again taking into account formal codified law, as well as the kind of state of exception even, or understanding when preferences allow for something to be so strongly desired that how and when it's pursued might not be how you'd pursue it in a different time. So there's just a lot of cool threads. Yes, Adam, and anyone else?
This is reminding me also from the first session, there was mention of value alignment. And like, this seems to be like a multi-scale problem in terms of like, it will show up just as much of like the robot not stepping on your toes or, crushing your foot, to like, as it expands, does it, is it optimizing in the direction, are its tensors going in the direction that you would want your tensors to go, of shaping? And it seems like of the proposals, sometimes there's, how do I say this, like begged questions that active inference maybe answers. So it's sort of like, let's say you have a framework like cooperative inverse reinforcement learning. And so there's some sort of like, it's like you are trying to like roughly like optimize for the utility function of the other agent. So how do you get this kind of like shared utility? But in like these like active inference models where like you're bootstrapping minds, like intersubjectively, you have like regimes of joint attention and thinking through other minds, or in some of this work with I'm doing with Anna Chianitsa, it's like she emphasizes how like we start out like actually physically inside of another organism, completely dependent, like homeostatically, and so like you're automatically sort of grandmothering in this joint intention right from the get-go. And the seeds of organization and individuation are already like scaffolded in that way, just by the by the niche contextualization, where you are co-constructing each other as your mutual. You and me, our intersubjective is like mutual niche construction. So it seems like with respect to I don't know at what point these problems in terms of like deploying robots when they first enter, because it's all all the way as highfalutin as like intelligence explosions. Will like a recursively amplifying system stay aligned with you? But just like in the world, how can I make sure the robot like doesn't crush my foot? Like anyway. So the ways in which co-valuing and the robot identifying itself as an individual relative to other individuals plays into it. It seems like active inference has like a very rich way of handling and modeling a lot of these different proposals and processes. But something I would wonder, like to ask like actual roboticists, like how near term is it like a live problem of getting like what forms of social modeling for robots, like, and what forms of like a sense of self modeling for the robot, like how much do we need at what stage for what levels of deployment in the world with what degrees of robustness? Simple question.
Yeah. Great question. And maybe just to double on what active inference does to potentially frame that junction, since in this roundtable we won't address, but this is the stuff and substance of applied active inference symposia for many years to come. In an economic framework, reward absolutist framework, which is kind of a full stack ranging from the ways that models are trained based upon pragmatic value and reward, all the way up through a world that values economic returns. The question becomes, in human-robot alignment, or in multi-agent alignment more generally, the question becomes, how are we creating and then allocating how are we creating and then allocating pragmatic value? And episteme can be valued to the extent that through time it provides pragmatic value. For example, one person doing a little bit more of a research angle and one doing more of an application and profit side of the business. And when we shift to a uncertainty imperative for a sustainable or even optimistic world model, then we can achieve pragmatic value as a consequence of a process theory that highlights reduction of uncertainty. And then the question moves from creating and allocating value to how can this ecosystem of diverse entities find a general synchrony and communicate and be how they are in a way that will be reducing the expected free energy of the ensemble, which is not the question that was even approached by the create value, allocate value framing that has come up in AI and continues to occur to this day. What if the image creators, what if they end up reducing our food allocation so they can have more? They take the intellectual property instead of providing it to humans. That might be framed slightly differently in an uncertainty reduction framework plus optimism, rather than in a reward maximization, which somewhat enforces a atomism and even a pessimism. We'll have, yes, Karl? Yes, please.
No, I just wanted to agree with you. That was an excellent point. Yeah. I mean, there are so many ways you can tackle that. I was still puzzling over Adam's challenge. How do you stop robots standing on your foot? I was thinking, how do you stop little puppy dogs weeing on the carpet? I think it's really, you've got to train them, haven't you, really? I don't think there's any magic answer. And I think the answer is just what Daniel said, things are designed and can presumably only exist under the free energy principle if they minimize their uncertainty or expected surprise so that they make everything as predictable as possible, which simply means that if I'm living in a world full of dogs, robots, cats, flies, and plants, then we're all trying to make ourselves as predictable as possible to each other. And that is that's a sort of folk psychological way of saying that variation-free energy is an extensive quantity. So if a set of Markov blankets or phenotypes of varying forms and structures jointly has its own Markov blanket, so it is an ensemble or a group or a community or a family, then it must put an upper bound on its surprise and free energy. And because the free energy of each constituent of that ensemble is summed to give the joint free energy, then it also requires that each individual is trying to minimize her surprise at the same time. It's all internally consistent and quite, to my mind, unmagical if you just look at it in terms of minimizing free energy or minimizing surprise under optimism, as Daniel nicely put it.
Thanks.
You just have to make your dog surprised when he wheezes. So you've got to find a way of making the robot surprised when he stands on your foot.
JF, you have a dog, right? So how do you see similarities and differences with these versions of, and also potentially even a family? So how do you see these different entities being communicating and behaving appropriately or not, and learning?
Well, having a dog, it raises the question of, do I make myself understood? And that's a very difficult question to answer. When I say no, you're not allowed to eat from that plate on the table, I think my dog understands. I'm not allowed to do this now. As soon as I walk out, then permission is granted. So it's difficult to communication is very difficult across individuals, especially across species. But I'd like to just rant a little bit on something which came up, which is the scale-free nature of free energy principle, the fact that it can apply at a societal level the same way that it applies, like a Russian doll, to the cellular level. As a software developer, I see self-similarity, recursion, fractal, as a beautiful thing, and I think the same way physicists have symmetries as a guide to what is right because it's beautiful, I think we share self-similarity as a guide as what is beautiful and possibly true. And I think self-similarity is beautiful because it collapses the amount of information that you need to generate something rich. So that's why I think that having a society of mind made up of actors and having a society of minds and having the same principles scale up feels very beautiful and feels right.
Excellent point. Yes, just if we could go for any length of time, a final set of thoughts and reflections from each of you.
Quick interjection, Jeff, if you have anything written on that or want to write it, there's an upcoming special issue on symmetries that I think it might fit with.
Would you like to give any final reflections or anything that you've heard or felt updated by? Any thoughts you have on the state of the applied active inference in 2022 in robotics, or where we're heading now that this symposium's behind us? I'll start with Adam, but then everyone else can go.
Thank you, Daniel. Well, this simulated a lot of questions, and just seeing the range of work being done was inspiring. And all I have to say is I was grateful to be a part of this. Thank you for putting this together.
Thank you, Adam. And
Yeah,
after the closing words, I'll review every presentation and list the co-organizers as well. So Bruno, and then we'll continue on.
Yeah, just like Adam said, thanks a lot for the invitation. It was very kind of you. I think I want to thank Mark Miller, that was insisting on us to to present with you here. It was a very nice experience, and well, we keep working. We need more hands. We have more ideas than hands, but I suppose that's everyone's problem, no? So yeah, thanks a lot.
Great. Then there were three. JF?
Yes. Well, again, thank you very much. This was extremely stimulating. Every talk I came out listening to it with this. I want to introduce in my robots some aspect of it, and my mind is buzzing right now with possibilities. And so, thank you so much for this opportunity.
I guess I can go next. Also, thanks a lot for being able to join this final roundtable and for all of the great presentations. I'll definitely have to look over them probably a couple more times to fully understand all the progress that has been made, and specifically on there's a lot to consider on the multi-agent modeling and the ideas in this discussion that we were also talking about quite a lot in the Active Block Inference project. Probably was left with more questions at the end of it, but that's also the exciting part of it. So thanks a lot.
And now it's my turn. I cleverly leave myself to last because everything that needs to be said has already been said. So that just means all I have to do is just to thank Daniel and his colleagues, which he's going to thank anyway, but personally to Daniel, thanks so much for all your energy, not just today, but over the years. It is really great to see these people and colleagues come together and sort of, generate ideas and questions, which is exactly what we need to do. Thank you.
Thanks a lot, Karl. And I think my one personal reflection, it swooped in at the end when JF said that from each of the presentations, there was like a module or an archetype or a function that transposed. And I think that is proof of concept of working in a shared ontology as well as in an embodied shared ontology, which is to say like a field and a community of practice with different small world structures and so on. But when we have the ability to transpose across systems and scales, then we can bring in the modules and the pieces that people are mentioning and start to understand how those functions can be composed and designed. And that's extremely exciting. Everyone, thanks for joining the roundtable. You can depart the Zoom, or I'm just going to review the presenters again and the co-organizers. So thank you for joining the roundtable. You can leave if you'd like. In the first session, there was Tim Schneider with Active Inference for Robotic Manipulation, Tim Verbelen, Robots Modeling the World from Pixels Using Deep Active Inference, Ben White, Artificial Empathy, Active Inference and Collective Intelligence, Noor Sajid, Learning Agent Preferences, and Wen-Hua Chen, Dual Control for Exploitation and Exploration and its Applications in Robotic Autonomous Search. Then in the first roundtable, it was Wen-Hua and I talking about dual control. The second session began with Bruno Lara with Prediction Error Dynamics, a proof of concept implementation, Matt Brown, real-time robotic control through embodied homeostatic feedback, and Adam Safron with generalized simultaneous localization and mapping, GSLAM, as unification framework for natural and artificial intelligences towards reverse engineering the hippocampal entorhinal system and principles of high-level cognition. And then JF Cloutier towards a symbolic implementation of active inference for Lego robots. We've just completed the second roundtable with Adam, Bruno, JF, Karl, Jakub, and I. The organizers for the symposium were Mark Miller, Matt Brown, Blue Knight, Alex Vyotkin, Ivan Metelkin, and myself. So thanks again. Till number 3 of Applied Active Inference. Hope to see everyone around the Institute.